The following message is best viewed on an oscilloscope.
Hello, everyone. Welcome to our second parallel session on top quark and electroweak physics. Today, we will kick off with some multi-bosons. Sun, could you share your slides? So Sun is our first speaker, and he will present on measurements of inclusive multi-boson production. I will stop my video to increase the sound quality, and Sun.
1 second.
We can hear you. Go ahead. Sorry? We can see.
Should I also start my video? Yeah. Okay.
If you want, yes, then we can see you. It's nice to see you at least a little bit. If the quality gets too bad, we can stop the sharing. I stop my video now. And I will mute and let you go. Thanks.
Okay. Hi, everyone. My name is Sun, and I'm here to give a summary of different multi-boson production analyses at Atlas. Okay. So we at Atlas had a great run too, with collecting 139 inverse femtobarns of data. And with this data, we have produced results on many different measurements. So here you see the summary for all the different diboson processes and triboson processes, and they're measured cross sections compared with theoretical predictions. Obviously, there's too many for me to cover here today, so I'm only going to focus on the three analysis on ZZ, WW, and Z gamma. The rest can all be found in our wiki, and I shared the link before, and if you're interested, please have a look. Okay. So the first measurement I want to talk about is the inclusive 4-lepton measurement. And this is a brand new result for this conference, and it was done with the full 139 inverse femtobonds. The goal of the measurement is to be as inclusive and model independent as possible, and it covers a very large N4L range from 20 GeV all the way up to 2 TeV. So there has already been a talk on it in the poster session from earlier today, which I gave the link here, and you can also find the conference note on the Atlas website here. Okay. So the basic idea is you want to select isolated high-quality muons and electrons, and then you want events with at least 2 E plus E minus and/or mu plus mu minus pairs. And if you have more than 2 pairs in an event, you select the 2 with the mass closest to the Z mass. The full list of selections is given here. There are some specific selections that target at suppressing specific backgrounds. But once you make these selections, then you get this histogram here. So on the x-axis, you see the mass of the 4-lepton system. And on the y-axis, you see the number of events. The black dots are the data, and the shaded histogram is the predicted amount of 4-lepton signal and background. So because it's such a broad M4L range, different production modes dominate in different M4L sections. So around the Z mass between 60 and 100 GeV in the green here, the dominant production is S-channel Z, where the Z also has a final state radiation that then also pair produces. Around the Higgs mass of 125, you are dominated by Higgs to ZZ. So that's what the blue peak is. And then above the purple line here at twice the Z mass at around 180, you get on-shell ZZ productions, both through Electroweak and through a QCD loop. And all the areas in between the areas I talked about, the dominant production mode is off-shell Z / gamma star. Okay, so you see good agreement between data and prediction across the entire range. And one of the things to note is that this pink background here, it's very important to make sure that we get the correct background predictions in order to make sure that our data and prediction agreement is good. Now, this background is actually mostly not composed of real 4-lepton events, but instead it's composed of processes such as WZ that produces 3 actual leptons. But then you get another lepton from a hadronic decay. So for example, like if you have a kaon or a B hadron that then subsequently decays into a muon, but then you misidentify the muons as coming directly from the interaction and not from a subsequent decay. So these backgrounds are called non-prompt lepton backgrounds. And the way we estimate the amount of these is by isolating Z plus jets events. So we select events with 3 leptons, where 2 of the leptons look very much like they come from a Z. And the additional lepton most likely originate from a hadronic jet. So using these events, we can calculate this fake factor by dividing the number of events with the isolated additional lepton by the number of events with non-isolated lepton. Then we can make a signal-like region, which has the exact same kinematic selections as a signal region, but we don't require all 4 leptons that make up the quadruplet to be isolated. So you can have a mix of isolated and non-isolated leptons. And with a number of these non-isolated events, we can apply the fake factor to get the estimate of how often you have isolated leptons, but the lepton actually comes from a hadronic jet. And on top of this, this is validated on other signal-like regions, which also have the same kinematic selections and requiring that all the leptons be isolated. But for example, you require that the charge in the lepton pairs to be the same. And because it's very difficult for standard model processes to produce same charge events, most of the events here are coming from the fake lepton. And if you see agreement in these regions, then it means that your predictions for fake leptons is good. Okay, so once we're quite sure about our background prediction, then we can calculate our fiducial cross-section, which is the number of observed events minus the expected number of background events. So essentially the expected number of signal events, and then you divide this by the luminosity and the correction factor that accounts for detector resolution and reconstruction efficiency. So essentially, if you observe one event, you actually expect there to be one event originally because you don't reconstruct every single event. And also the resolution can cause your event to shift around in the bins and stuff. So you want to take into account the resolution. The end result is the plot on the right, where again, you have M4L on the x-axis, and now on the y-axis, you have the differential cross-section, d sigma dm4L. Again, you see good agreement between prediction from Monte Carlo and the measured data. So aside from the M4L differential cross-section, we also measure differential cross-sections with respect to many different kinematic variables. So they're listed here. I'm not going to go through each of them. But the important thing to note is that the different differential cross-section distributions is sensitive to different beyond the standard model physics. So for example, the decay angles are very correlated with the polarizations of the bosons. And if you have some BSM physics that then change that, then you would only see it, you would see it in the decay angles. Okay. So one beyond the standard model interpretation that was also given as part of the paper is this baryon number minus lepton number symmetry interpretation. So B minus L is a conserved quantity in standard model. And what this theory does, it introduces another U1 gauge symmetry on top of the standard model gauge symmetry. And this symmetry is broken with another Higgs field. If that Higgs field and the standard model Higgs field have mixing, then what you can do is you can produce additional Z primes that then decay into leptons. And so this will contribute to your 4-lepton cross-section. So on the plot on the right, what you have is on the x-axis, you have the mass of the second Higgs. And on the y-axis, you have the mixing angle between the standard model Higgs and the B minus L Higgs field. And the area above the red line is excluded to 95% confidence. So this area phase space is excluded. Okay. Okay, the next measurement I want to talk about is a measurement on Z gamma production cross-section. This is another measurement with a full 139 inverse femtobarns of data. And this was published in March of this year in JHEP. So again, here you select for good electron muons and photons. And then you have these kinematic selections to essentially isolate photons, which are part of the initial state radiation, alongside requiring there also to be a Z. So what I mean is showing in this plot, on the x-axis, you have the mass of the triparticle system, and on the y-axis, you have the mass of the lepton system, so mu mu here. And what you see is you have two distinct populations. Down in the lower left corner, what this is Z bosons that also emit another photon as part of the final state radiation. So you see the triparticle system peaking at the Z mass here. And for this population, you see that it's a Z boson that's produced in conjunction with an initial state radiation photon. And therefore, you see that the triparticle mass is now greater than the Z mass. But the dimuon mass here corresponds to the Z mass here. And what this selection does is that it essentially cuts along this diagonal line and accepts only the population above the diagonal line. So we want essentially the initial state radiation population because the final state radiation should count towards just a single Z production. Once you make the selections, you get the signal region distribution here with the mass of the three particle system on the x-axis. So yeah, this is dimuon, this is dielectron. And again, you see good agreement between data and prediction. The dominant background here is again Z plus jets, where the jet is actually misreconstructed as a photon. And I'm not going to go into detail here. The method for estimating this is analogous to the one I just talked about before. But you see here that the leading order Sherpa is scaled up by 1.23. This is actually about the scale factor that you would get between the difference between next leading order and leading order. So you're just essentially correcting for the next leading order correction here. So it's not an actual misprediction. Okay, so again, you measure the fiducial cross-section in the method I talked before. You subtract the background and take into account the detector resolution and reconstruction efficiency. And you get that the total fiducial cross-section is 533.7, which agrees well with our highest, most precise predictions between these two simulations. So on top of this, we produce different differential cross-sections in all these different kinematic variables. The one that I want to draw your attention to is the transverse energy of the photon. And the reason for this is the photon energy correction is actually large at next to leading order electroweak corrections. So as of now, we have both theoretical calculations for the next leading order electroweak corrections and the next leading order QCD corrections. However, there's been no complete computations of how to combine the two corrections together. So right now there's two methods that are used. You either combine the two additively or you multiply the two corrections together. And you actually see that the data agrees better with the additive approach. So this is interesting because this is the first time essentially where you can see a difference between the two approaches. And this seems to do better, agree better with an additive approach. Okay. Finally, I want to talk about the WW measurement done with 36 inverse centilbar data. And this is a bit older. It was published in October 2019, but I'm covering it here today. The idea here is you select E mu events, so 2 leptons of different flavors, because this rejects Giulia and Z events where they're the same flavor. And on top of this, you reject events with high energy jets and high energy B jets specifically. This is because the major background here is TT bar and TW, where the top will produce a B and potentially other jets. So here, again, the result, we get a fiducial cross-section of 379.1. It still agrees within uncertainty to theoretical predictions, but as you can see from the table of theoretical predictions here, it's all on the lower edge of the 1 sigma agreement, essentially. Okay, so once you go into differential cross-sections, you see that from some differential cross-sections, for example, here, this is a delta phi between the 2 leptons. And this is the PT of the most energetic lepton. That the Monte Carlo all agree with one another, but they seem to disagree with data at some specific points, like for example, around delta phi 1.5, and at low leading lepton PT here. It's unknown why this is, and it's not sure how, I guess, significant this is because the global chi-square over degree of freedom difference is still small. So if you calculate the chi-square difference between prediction and data, the biggest difference you see is 18.5 divided by 14, which is still somewhat consistent with 1. But I just wanted to point this out. Okay, so finally, the WW measurements have puts limits on the anomalous triple gauge couplings. So you can have additional dimension 6 operators here that involve either 3 bosons or 2 Higgses and a boson. And the analysis set limits on the coupling coefficients here, and you can see them in this table. So in conclusion, there's lots of results and measurements coming from Atlas, and there's many worthy analysis that I could not cover here today. ZZ, WZ, for example, and I gave the link to the analysis here. So yeah, please stay tuned for more updates in the coming month, and bookmark our Twiki. And that's all.
Thanks a lot, Sun. Are there any questions or comments on these results? Anyone curious about some aspects of the measurements?
One quick question, perhaps. So, what was the total? Did you have like a total cross section for ZZ, and what's the precision on that right now?
Because it's an inclusive measurement for, it's not just ZZ, right? It's also inclusive for Higgs. It's essentially this entire line. It's not particularly a ZZ measurement.
I see.
Yeah, so they do have an interpretation for the branching ratio of the Z to 4 lepton. That's part of the paper, and
Oh, okay.
I also have a speaking the measurement.
I'm sorry, it's very difficult to hear. I don't know if it's just me or.
No, it's same here. Actually, we can't hear you. Your video, audio is very choppy, Fabio.
I'm sorry. If I'm luckier, yeah.
Try the group chat, and we will read it out, please. Okay, Kenneth, have you raised your hand? Would you like to ask a question, please?
Yeah, can you hear me?
Yes, we can hear you.
Okay, great. So, yeah, thanks for the nice talk and these nice analyses. You mentioned for the Z gamma, the sensitivity to the next leading order electroweak corrections. This should also be there for the ZZ to 4L. In particular, maybe the 4 lepton mass. At high mass, you would expect to see some fairly significant corrections in a low electroweak. I'm wondering if you looked at that. I mean, just looking at slide 8, I don't really notice any dip that you might expect from next leading order electroweak at high mass, but it's not trivial to just look at the plot and tell. Thanks.
I don't think there were any significant differences that was seen. Yeah, I'm looking at the paper now. Yeah, I don't think there were any significant differences that was seen.
So in principle, one could make the same comparisons with the fixed order predictions on the unfolded cross sections. Do you know if there's any plan to do that? As was done for WW and Z gamma.
Sorry, I'm looking now. I think they do this. Let me see.
Maybe, sorry to cut this short, maybe we'll take this question offline. I hope you're both on MetaMost, so go to this channel that we can have this discussion. I would like to take, there's one last question from Fabio Maltoni, and he wants to know whether the gamma measurement was inclusive over jet radiation gamma Z.
Ooh. I don't know off the top of my head.
Okay, so again, perhaps something
I
that
believe it's jet radiation. You mean like a jet radiating a gamma? It's rejected, I believe.
Okay. Again, maybe
I'm still sharing, right? So if you look here, processes such as D are suppressed because you have isolation requirements on the gamma.
Okay, good. Then again, this is something that we can also discuss in a little bit more detail in the MetaMost channel. I will post it in a second. But for now, let's thank the speaker again. Thanks, Sun. And we will move to the next presentation, which is by Philip Chang on the search for heavy triboson production in leptonic final states with a full run-through at CMS. Sun, if you could stop sharing, then it's your turn, Philip.
Okay, let me share.
Yes, we can see you. Hi. And the sharing. Brilliant. Thanks a lot. Just start and go ahead. Thanks.
Okay. So I'm Philip Chang from UCSD, working on CMS experiment, and on behalf of CMS collaboration, I will present today the first observation of production of 3 massive gauge bosons. As we all know, the discovery of the Higgs boson was a big triumph of the LHC physics program. It advanced our knowledge of origin of mass in a major way. But there are still many questions to be answered in the Standard Model, and in particular, to list a few, there are several questions in the electroweak sector of the Standard Model that we must study, such as, is the Higgs boson we found the Higgs, and is it the only Higgs, or are there more? And also, are the multi-boson interactions all Standard Model-like, or if they have any deviations to it? Or are there more states that couple to the electric sector, modifying the couplings of these multi-boson interactions? And if so, what are their role in the electric symmetry breaking? And of course, we have the question of how the Higgs potential look like, and whether it is Standard Model-like, or if they have some more structure to it, which have a very deep implications in cosmology or baryon asymmetry problem as well. And by studying the quote-unquote massive bosons of the Standard Model, such as the W and Z, and of course the Higgs boson, many of these questions can be studied. And one thing that I want to say is that oftentimes when we say multi-boson interaction or production, at least I think between the experimentalists, I believe we tend to talk about the W and Z bosons only, but I think that going forward, we should really start referring to the multi-boson interactions or productions of all of these massive bosons as a whole. So this gets me to the topic of today, which is the triboson production. The triboson production is interesting because it involves many types of multi-boson interactions. The process involves cubic, quartic, and Higgs gauge interaction type of multi-boson interactions. And here the V represents both the W and Z, and therefore there are 4 types of VVV production, namely the WWW down to ZZZ. And for today, we're covering all of these production modes as a whole. So in the past, both Atlas and CMS have been searching for triboson processes, and both have first started with the WWW. And Atlas started the effort in ATV, and then subsequently CMS followed in 2016 for 2016 dataset. And last year, Atlas reported a first evidence for VVV combined triboson production with partial run-through dataset. And the search's results were used to place constraints on new physics, targeting, for example, a specific model with triboson new physics, or via the limits on the dimension 8 operators of the Standard Model effective field theory framework. So to quickly recap, for today, what we're targeting is that we're continuing on the quest to search for the VVV production modes, targeting all 4 VVV production modes individually, and also the combined production of the VVV. And so in other words, we'll have a results for all 5 signal definitions. So to start the discussion, here is a plot that shows a cross-section in y-axis, and the x-axis have the 4 different production modes. And as you can guess, majority of them will decay to 0, 1, or 2 leptons. But these final states are quite difficult. So that's not where we want to be to make a first observation. So really the viable channels of the triboson production for making a first observation are when the triboson fully decayed leptonically. So in fact, we focus on the final states for 3, 4, 5, and 6 leptons. In addition, we also consider the 2 leptons same size, but especially because it has a small have manageable backgrounds. And these final states are very rare. And as an example, the ZZZ to 6 leptons, the cross-section times the branching ratio is 11 attobarn, which means that it would have been something like 1.5 events produced at the run-2 of LEC. So it really demonstrates here that, this is why the triboson analysis is just becoming accessible at the LEC and will be more relevant going into the future. And to do these many lepton physics, so to speak, we need to have an excellent reconstruction of these leptons. And CMS detector can measure these leptons very well. Leptons are among the best measured particle at CMS, and it does so by combining tracker, calorimeter, and muon chambers measurements, and we achieve something like 1 to 2% resolution of the leptons. And as a demonstration here at the bottom, I'm showing you a Z to mu mu resonance reconstruction of data in simulation. And at the bottom panel shows the excellent agreement between data and Monte Carlo simulation. So this shows that we can measure them very well, and also we can simulate and understand them very well. So the first step to the analysis is to categorize the events by the number of leptons. So this, first of all, is advantageous because it separates each triboson production modes into a different bins of number of leptons. For example, in 3 lepton bins, so primarily it'll be the WWW. In 4 leptons, you have WWZ, and so on and so forth, down to 6 leptons. And especially as in one exception to the cases, the same sign dilepton, which is primarily targeting WWW because that's the only one that produces the same sign, but one of them will decay hadronically. And once you bin by the number of leptons, not only the signals are separated, but also the sources of the backgrounds become well separated, and it becomes somewhat obvious what they are. So primarily in each lepton channel, the diboson processes are the dominant source of background. So for example, the 3 lepton, you have the WZ to 3 lepton being the major background. And in the 4 lepton case, you have the ZZ to 4 lepton being the major dominant backgrounds. And then the second type of dominant backgrounds are the ones with TT bar or TT bar plus X, like W or Z, which comes as the extra B quarks in the event, which you can suppress further by requiring that the events do not have any B tag jets in the event. One more thing to quickly mention is that there are some signal cross-contamination between the leptons because some of these production modes can produce different types, number of leptons, which we deal with these at the final fit, but they in the end have a negligible impact to the analysis. So to further suppress the main backgrounds in the of the analysis, which is the diboson backgrounds, we've been further by the flavor of the leptons. For example, for the 3 leptons, if the 3 Ws that you have decay in a configuration where you have a same sign electron plus an opposite sign muon, then none of the pairs in these cases will make up a same flavor opposite sign pair, which could be a Z candidate. So in this kind of 0 SFOS configuration, the WZ process, which is a major 3 lepton background, is highly suppressed because it would have to come through a cascade decay of the Z to 2 taus and then to the E mu's, and with neutrinos taking away a significant amount of energy. And so there's a branching fraction to tau to leptons, and then also the fact that they're soft, the acceptance is smaller, and so your WZ backgrounds are highly suppressed. And a similar thing happens for the 4 lepton final states, where once you tag a Z, by requiring that you have an E mu pair, 2 additional leptons in the E mu, it means that the ZZ background will then have to go through the cascade decays of the Z to tau tau, which then ends up having a suppression in the background significantly. So this is one of the major way of reducing your backgrounds. And so we organize our search not only in the bins of leptons, but also by the flavor of the leptons. And so for the 3 leptons, you have split by the number of same flavor opposite sign in your configuration of your final states. Obviously, the 0 SFOS will be the cleanest one. Now, for the 4 lepton channel, it's also organized by, after tagging the first Z, you then split by the same flavor versus a different flavor in your 2 additional leptons that you have. And which, in the cases for the WW then decaying to E mu, you'll have a smaller ZZ background. And for the same sign dilepton channels, we separate them by flavor of EE, E mu, mu, mu. And this is because even though standard model respects lepton universality, the detector basically ignores them. And so the muon is generally quote unquote cleaner than the electrons. And so that we separate the number of same sign dilepton events by the flavor. For the 5 and the 6 lepton, there's not enough statistics because these are very rare, as I've mentioned before. And so we have just a single bin category. So then one more thing to add here, for the 2, 3, and 4 leptons, we have a dedicated BDT analysis as well, which I will briefly discuss in the coming slides, but I won't go into much more detail. So once you then separate your events by number of leptons and by the flavors, and then the next step that you do is to, for the same side channel, the target signal is 3W. But one of them will decay hadronically. And so, and since jets are a bit harder to reconstruct, we allow total of sort of 3 categories where we have the dijet with an invariant mass near the W mass, which would be MJJ in category. And then we also allow for additional cases with the MJJ, with the 2 of the jets are not matched correctly to the Ws. And so it may have a wider MJJ distribution. And also the cases when one of them were lost because it was soft and it was not part of our acceptance. And so we have 3 additional categories: MJJ in, out, and 1 jet, where each of them are also again split by EE, mu, and mu, as mentioned before. And so for the same set analysis, we have total of 9 signal regions. Then for the 3 lepton analysis, the targeted signal is again the 3 Ws. And as mentioned before, the 0 SFOS is the one that has the cleanest channel because it reduces the WZ backgrounds. For the 1 SFOS, we can do a bit more things because for 1 SFOS, it is clear which lepton is from the W, because the one with the same flavor opposite sign pair must be coming from the Z if you have for background events. And then the third one, the odd one out must be coming from the W. And so if you plot the transverse mass from the 3rd lepton, then you'll see a clear, the transverse mass of the W as the classically known, and you can place an end cut here and reduce your WZ background significantly. And there, similar strategy can be applied for the 2 SFOS, albeit a bit differently. And at the end of the day, we have 3 signal regions in the 3 lepton final states. And as mentioned before, the same sign in the trilepton analysis also have a dedicated BDT analysis for each categories of events using these kinds of kinematic variables that I just mentioned here, which I will not discuss in details, but I'll leave it at that. Then for the 4 lepton analysis, which primarily targets WWZ process, and for the reasons explained before, the Z plus EMU pair is the one with the cleanest channel. And to further suppress your ZZ background, we use a generalized transverse mass variable targeting multiple missing particles called the MT2, which is sensitive to the endpoints. For example, in this kind of configuration, it will be sensitive to the tau mass, and in this case, it'll be more to the W mass. And so for the ZZ background, it'll pile up at the low value, and then for the WWZ background, it'll have a longer tail. There are additional variables that also exploit the differences between WW decay to Z to tau tau, and all of those variables are combined together to create a cut-based analysis with for the 4 lepton analysis and create a 7 bins analysis. But we also then use all these variables, and then we trained a dedicated BDTs analysis for the 4 lepton as well, just like the same sign dilepton in the 3 lepton case. And we trained the WWZ signal against the TTZ and then the ZZ background, which are the 2 main backgrounds. And the plot on the left shows the 2D discrimination sort of in action, where the red dot distribution shows the ZZ background piling up towards the left, because the x-axis is the BDT score of the WWZ versus the ZZ. And then the TTZ background piling up on the bottom portion of the plot, because the y-axis is the score for the WWZ versus the TT bar Z, and in the top right corner has a clean green dot distribution, which is our WWZ signal. And then we have done some optimization to create a binning choices and created 5 bins for the analysis. And the right-hand side shows us 5, 1, 2, 3, 4, 5 bins, and whereas you go towards the right, it becomes more and more cleaner. A similar step was taken for the other remaining 4 lepton analysis channels, and then eventually we've got a total of 7 signal regions for the 4 lepton analysis. Then for the 5 leptons, which was targeting the WZZ process, since the signal contains 2 Z's, we require that events have 2 same flavor opposite sign pair consistent with the Z mass. And so that the dominant background is your ZZ to 4 lepton, then plus one fake lepton. And the reason why there's no major background producing true 5 lepton is because the dominant standard model process with 5 leptons is actually the WZZ process, which is our signal. And since the fake lepton it has a low transverse mass, while the signal coming from the W to the lepton will have a high transverse mass, we plot the transverse mass distribution, and then we place a cut there to reduce the ZZ background. And since there are not that many events, we do a single bin of cut and count experiment for the 5 lepton. Then for the 6 lepton, it's even more, we do it even, it's extremely cleaner, but it's, there's very little number of events. And so we target it very inclusively of 6 or more leptons, and then we have a single bin. But we require a bit of a high sum PT of the events. And we expect less than 1 event, but the purity is about 90%, so it's very clean. So there's only 1 bin total for the 6 lepton. So then putting it all together, we get total of 21 bins to bit. So to quickly recap, that we have the 5 lepton bin category. We have a split in flavor for 3, 3, 2, 1, 1. But then we further split for the same sign dilepton and the 4 lepton cases using kinematic variables and the VDTs and etc. And then eventually we come down to 21 bins searching for the triboson production, and also different bins represent are primarily targeting different VD production modes like the WWW versus WWZ and etc. So then moving on to the background estimation. For the background estimation, the key here is to reliably extrapolate across the method used to suppress the background to estimate the size of the residual backgrounds in the signal regions. For example, the fake lepton backgrounds are suppressed by applying a tight isolation in your leptons. And so to estimate this really, what we need to do is reliably extrapolate across isolation. Similarly, with the backgrounds with B jets, we require that there's a small number of B tag jets. So we're suppressing it by B tagging, and therefore, in order to estimate your background, if you reliably extrapolate across the number of B tags, and then you will be able to estimate your background. Similar things happens for other types of backgrounds. This is how we would do it. And I will just point out just a couple of things without going too much into details. First is that the fake lepton backgrounds. So the fake lepton backgrounds are crucial for the same sign in the 3 lepton final state. It has the most fake lepton background contributions in comparison to the other backgrounds. And as explained before, the key here is to extrapolate across the isolation variable. And the extrapolation factor across this isolation variable tends to be difficult to model via the Monte Carlo because it needs to have a reliable modeling and simulation of the leptons coming from jets, originating from jets, etc. The method described here is kind of similar to the method that Siyuan just mentioned from the previous talk, but instead of measuring these rate of the fake leptons passing your tight lepton isolation, we measure, instead of from Z plus jets events, we measure from the QCD events. And we pick 1 lepton events with the phase space dominated by QCD dijet events. And for example, here is showing an event display of a dijet event with one of the lepton embedded in the jet. And you take a bunch of these kinds of leptons, and then you ask and measure the rate at which these passes my tight isolation. And then from this sample of events, we measure the rate of how often.
Could I ask you to slowly wrap up a little bit?
Oh, okay. I will do this quickly. Okay. So we call this a fake rate, and then we apply this fake factor and to measure our fake background estimation. And the uncertainty tends to be something like 30%. It's quite difficult to reduce them further. And for the other backgrounds, it's generally quite straightforward, where we would invert the B tagging, and then we would construct a control region with the high number of B tags, and then we extrapolate across the number of B tags, which tends to be about 10% uncertainty. And then for the other types of analysis, other types of backgrounds that were suppressed based on the flavor choices, we extrapolate across flavor, and the uncertainty tends to be about 5%. And so here is then the final result, putting it all together. We see the 9 bins of the same size signal regions, the 3 bins from the 3 leptons, and the 7 bins for the 4 leptons, and then the 1 bin each for the 5 and the 6. You can see the different colors for different triboson production mode, the red being the W and the green being the WWZ. And in the most sensitive bins, you can see the clear presence of the triboson productions, like the green here and then the green here and then the red above their backgrounds. And the bins are ordered somewhat by physics motivation, such that the more sensitive bins are towards the right in each category of the events. I'm going to skip these 4 lepton and the 5 lepton event display that I placed here. You can take a look at them at your leisure. So the final result, we have observed for the combined production mode, we have a over 5 sigma. So we have observed the production of 3 massive gauge boson for the first time. And we also found evidences for WWW and WWZ individually for above 3 sigma. And we've measured the signal strength for the individual and the combined, which are consistent with the standard model and expectation. And if you focus on the statistical uncertainty of the measured signal strength, they're statistically limited. And so as you have more luminosity, it'll get better in the future. So this takes me to the summary slide. So I think I've mentioned everything, so I'll stop here.
Thanks a lot, Philip. I'm sure there are a lot of questions for this very nice result. And just to say, I unfortunately cannot see raised hands, so I'll rely on my co-conveners to tell me. Okay, Philip Sommer.
I have raised a hand, yes. Hello. So I have a question on slide 16. So it's I find it very impressive how uncorrelated these two PDTs are. So can you say a bit more if some specific measures were needed to decorrelate them, or for example, do they use different variables? For example?
So for the ones for the WWZ and the TTZ have small. It does have a different choices of variables, but also they were trained differently. Meaning, the y-axis was trained against WWZ and TTZ only, and then the x-axis was trained against WWZ to ZZ only. And so I would say that's why it was highly decorrelated. So it's a 2 different BDT training with the 2 different sets of variables, one targeting against different background separately.
And then do they share some variables?
They do share some variables, but there are some additional variables for TTZ. And I have to remember, there was about 10 or 12, so I can't remember off the top of my head right now. But for example, for the TTZ, there are a bit more jet variables. For the WWZ versus ZZ, they're primarily the differences in the Z to tau tau decay versus the WW decay. And so that one is generally lepton oriented, lepton emitting ET final states, and there's not really, jet doesn't really have any kind of discriminating power. But for the TT bar Z, if you have an additional jet, the delta R between the jets and the leptons and etc. Adds up into your discriminating power. And so for the y-axis here, where it's trained against TTZ, have additional variables with jets included.
Okay, thank you.
Okay, any further comments or questions? Maybe you can flash the results slide again.
Sorry, I couldn't hear you very well.
Sorry, I said maybe you can go back to the results slide.
Summary slide, you mean?
Yes.
Okay.
Okay. So I guess you will repeat the analysis in run 3. So I mean, no hints for ZZ is expected, right?
Right. So for the ZZZ, we didn't get anything. So I think for run 3, it'll be interesting to look at the 5 and the 6 lepton, definitely. But even now with the remaining run 2, we're currently working on the semi-leptonic final states because those are the ones that I initially mentioned that it's a bit harder, and so we haven't done it. But for the other 0, 1, 2, or maybe even 3 leptons with semi-leptonic final states, so you can have more acceptance to these kinds of signals. And then the fact that now we've established these evidences and the observation of processes, I think we can look for like PSM effects at the high PT tails for semi-leptonic final states. And so those are some of the things that we can already do with Win2. But with Run3, certainly we should be able to do better since these are statistically limited.
Okay, thanks a lot. Great. If there's no more questions, then I think we will move on to the next speaker. There's still the possibility to discuss on MetaMost, of course. Thanks again, Philip. And now we will have a presentation from Mariola Kłusek-Gawenda on photon-induced processes.
Moment.
Okay, we see your whole screen.
Yeah.
So,
moment. Okay, do you see my presentation now?
we see you. I don't see a presentation yet, sorry.
So moment, so share screen.
That is again more or less everything. Yes, now it's full screen, your presentation. Okay. Thanks. I will let you go. Please go ahead. Thanks.
Okay. Thank you very much. So good afternoon. I hope that all of you are well in the age of pandemic. So I would like to present you my study, my results about the light-by-light scattering in heavy ion collisions, in ultra-peripheral heavy ion collisions. I would like to present new results and some prospects. And I based on 3 published papers and 1 study which was reported in this report of the yellow report. I would like to talk about the ultra-peripheral collisions. That means that distance between 2 nuclei is bigger than the radii of 2 nucleus. So at the beginning, I would like to talk about equivalent photo approximation. Is the approximation which allows to calculate the nuclear cross-section, the total and differential cross-section. Next, I would like to go to the light-by-light scattering. I will focus on the elementary and nuclear cross-section. And finally, I would like to show some results for electromagnetic excitation and conclusion. So as I mentioned, I would like to focus mainly on the ultra-peripheral collisions. So one can see one can imagine fast-moving nuclei with the charge Ze. Due to the coherent action of all protons in the nucleus, ions are surrounded by a strong electromagnetic field. And this field can be viewed as a virtual photons. Why virtual? We can say that there are real photons because the virtuality Q² is smaller than 1 GeV. So this value is very small, so we can treat photons as real. So photons can collide with each other or with the other nucleus, producing some final state. So if you would like to calculate the total cross-section for this process, we should take into account at least 5-dimensional integration. But in our calculation, we extend this equation usually to 2 or 3-dimensional the additional dimensions, because we would like to have the control over the full kinematics of the process. I mean, here we have the integration over the rapidity of the first and second outgoing particles, or PT of the particles. So if you would like to calculate the total cross-section, you should know the probability that from the first nucleus, some photon with the energy of ω1 is emitted. You should know the probability that from the second nucleus, some photon is emitted with the energy of ω2. And additionally, you should know the probability that both photons collides with each other, producing some final state is X1 and X2. Here we have some additional factor is the absorption factor, which ensures that we include only peripheral collisions, only ultra-peripheral collisions. This means that nuclei cannot touch even, okay? So here we have the integration over impact parameter space. Bx and by are the components of Bx and by are the components of B1 and B2 vector, where here we have the point where new state is produced. Integration over the invariant mass of the outgoing state and rapidity of the xy and x2. The photon flux very strongly depends on the form factor, but people very often use a different type of the form factor. Very often the point-like form factor because of the simplicity, and the point-like form factor is constant equals to 1. In our calculation, we use so-called the realistic form factor, where the realistic form factor is the Fourier transform of the charge distribution in the nucleus. So I think that this figure is, with the help of this figure, I can very easily explain how the difference between the realistic and monopole form factor. So here should be the line for the point-like form factor. And next, we can see that when we have the form factor is a function of Q, that only in the very limited range of Q, the difference between the realistic and monopole factor is almost 0. But with larger value of Q, the difference between the realistic and monopole factor becomes larger. One can see a lot of oscillation, which are characteristic for relatively sharp age of the nuclei. So as I said, the total cross-section, if we would like to calculate the total cross-section, we should have the elementary cross-section. So in our calculation, we include, of course, well-known the fermionic boxes. We include the boxes from W boson, and I think that this figure is better to explain the difference between the contribution. So we can see the contribution from leptons, the purple line, from quarks, so the sum of lepton and quarks. So we have the fermionics contribution. And here we have some contribution from W boson. Of course, this contribution is important only for rather high energy because of the mass of this boson. But you can see that this cross-section is relatively small because here we have 1 MeV. So for 1 MeV, this cross-section is about 1 microbar. For 1 GeV is about 10 nanobar. So the cross-section for light by light scattering is very small, and that's why it's really very difficult to measure just this process. So in our calculation, in our study, we include 2 additional processes. The first one is the VDM-Regge model. In the VDM-Regge model, here we have the fluctuation of 2 photons into some hadronic state, where we have the vector meson, light vector meson. We include 3 different light vector mesons, I mean rho, omega, and phi meson. And next one, we have 2 gluon exchange process. This process, in fact, is 3 loops because here we have the gluon exchange. And in fact, we should include 16 different diagrams because different couple of gluon. So let's look at the contribution from boxes, VDM-Regge, and 2 gluon exchange. So here I show the differential cross-section as a function of cosine theta and as a function of pt. And it's given for fixed value of the energy is 10 GeV. And you can see that the VDM regime contribution is very important only in very limited range of Z. The box contribution dominates over all processes. But let's look at the two-gluon exchange, I mean this new process. You see that here we have two lines. Why we have two lines? Because we, in the first line, we include the situation when the mass of gluon is 0, but we know that we include here the situation that we cannot have the W counting. So here we have the contribution when the parameterization of gluon, I mean the mass of gluon is 0.75. So we can see that it's really rather difficult to find some range of the PT where the two-gluon exchange wins. So let's look at the larger energy. So we can see that at the energy of 200 GeV, we have some possibility where two-gluon exchange wins, but going to the smaller energy, it's rather difficult to observe, to identify this process. So it's the questions that maybe from the experimental side, the International E+, E- linear collider should evidence just this process for the first one. As I said, I would like to focus on the ultra-peripheral collisions. So now I would like to show you the differential and total cross-section for ultra-peripheral, ultra-relativistic lead-lead collisions for the energy LHC, for the LHC energy. So you can see the differential cross-section is the impact parameter. So here I should mention that this distribution is critical. I mean, the distance between two nuclei cannot be measured from the experimental side. So here I would like to show you mainly the difference between the monopole and realistic cross-section. So let's focus on the contribution for boxes. Here you have two lines. The blue line is for the monopole form factor, and red line is for the case when we include the realistic form factor in the calculation. So you can see that with larger value of the impact parameter, the distance between realistic and monopole form factor becomes larger. The situation looks very similarly when we go to the distribution in the rapidity. So I think that next slide should be more useful because here you have the total cross-section. Here is the table for different cuts on the kinematics. And there is the total cross-section for boxes for VDM region in nanobar. And you can see that the difference between the total cross-section between the realistic and monopole form factor is about 50, maybe 20% when we compare the realistic and monopole form factor. And the situation looks very, very similarly for VDM region. But when we go, when we make cut on the PT, for example, then we can say that we remove the VDM region contribution. So you can see that, for example, when we look at the mid-rapidity, the difference between the boxes and VDM region is not 2 order of magnitudes like in this case, but is about 4 order of magnitude. So with the help of this table, I would like to show you that the total cross-section or the importance of the VDM region model very strongly depends on the kinematical variables. And I would like to show you that if we would like to have, if we would like to prepare the exact prediction for the experiment, we should take into account all possible conditions, I mean, all possible realistic conditions, and I think that we should take more realistic form factor. About 3 years ago, the Atlas collaboration has published the first paper. It was the first measurement of the light-by-light scattering in ultra-peripheral collisions. So they evidence only 13 events for light-by-light scattering. And here we have the experimental point as a function of acomplanarity and invariant mass. And here it's very important to mention that, note that the Atlas collaboration has measured this process from 5 GeV, I mean the invariant mass. It is for the mid-rapidity. And when we compare the results, this one, the 70, ±20, ±70 nanobar, with our results, is just this red line on the figure, we have rather good agreement with the experimental results. But 2 years later, after the first evidence, the Atlas collaboration observed almost 70 events. The total cross-section is a little larger, but the error is smaller. So of course, we have to compare just this number with the experimental point, because this cross-section and this one is calculated, it was a measurement for exactly for this range of the kinematical variables. In the same year, the CMS collaboration made the first measurement of the light-by-light scattering for smaller value of the invariant mass. It means it's for 5 GeV, not 6, because Atlas collaboration has measured this for 6 GeV. And the cross-section is 120 nanobar, but the error is relatively large. I recalculated this process for this kinematics, and I obtained 103 nanobars. And in my calculation, this error comes only from the Monte Carlo code, but not from, I don't include here the error from the monopole on realistic form factor. But if you would like to do this, you should calculate that this error should be about 20% of the total cross-section. You would like to calculate the situation when monopole form factor is included in the calculation. But next, very recently, the Atlas collaboration has published, but maybe not published, but it was presented recently during the LHC conference. And this result will be discussed tomorrow by Mateusz Dynda, just on the same session. So here we have very fresh data for the Atlas collaboration, for the Atlas group. And here we have the measurement from 5 GeV. So the Atlas collaboration obtained the cross-section equals to 120 nanobar. And I have recalculated this process for this kinematics, and I have 90 nanobar. So we can see that we are missing something. So now is the question, what we are missing. So next slide, I would like to focus on possible processes. Maybe the answer is maybe we should include the contribution from two-gluon exchange. Although we see that this cross-section is about 2-3 order of magnitude smaller than from the leptonic boxes, but maybe if we calculate the coherent sum of both processes, so maybe then the cross-section should be a little larger. And the other way is maybe we should include the pionic boxes, but it's rather difficult to calculate just these both boxes. So it's the open question and open study. So I think that we should do this. So next, I would like to go to the situation when we focus on the invariant mass smaller than 10 GeV. because we know that for the energy larger than 5 GeV, not 10 but 5 GeV, I'm sorry, the
slowly time to wrap up, sorry.
Sorry?
It's slowly time to wrap up.
Okay, okay. So if you go to the smaller energy, we are sure that we should include some contribution from mesons, exchanges, and background. And we see some enhancement in the mass very close to the pion or eta and eta prime. And we have really very good description of the process for gamma gamma to pi 0. It's our fit, the physical fix, not only mathematical fit. And here we include the situation that when from first pion, the two photons are emitted, are produced, and we take into consideration only one photon, and second photon is taken only from the second pion. So we see the differential cross-section for ALICE and for LHCb cuts. The ALICE is for mid rapidity, ALICE cut for more forward rapidity, and some additional conditions on the PT. And we see that we see large cross-section, large peak just for eta and eta prime, but here we have unwanted background. So maybe I will skip this table, but you see the total cross-section is the larger for eta and the next for background when we focus on the energy below 2 GeV, but for larger than 2 GeV, we have the clear situation, the boxes wins, the contribution from box wins. So we try to find some way how we can reduce this unwanted background. So the first way is maybe we are sure that we should include the energy resolution, and then the cross-section, total cross-section is of course the same, but the peak for ALICE cuts is about 2 orders of magnitude smaller. We have broader resonances. And next one, we look at the PT sum, and we see very small change when we will obtain the situation when signal overestimate the background. So we include something like the scalar asymmetry, and the scalar asymmetry to 0.02, the 80% of signal events is just in this object, in this area, but for background is about only 5, maybe 8%. So when we imply this cut on the differential cross-section, we see that the cross-section is larger than 1 order of magnitude smaller. So we see some situation when we have the importance of the signal and cut this background. And next one, I have the prediction for argon, and even when the cross-section for argon in the comparison to lead-lead collisions is smaller because of this ratio, then for run number 5, we predict the signal of events order larger than 1 event 4,000. So last slide, I would like to only mention that we can calculate the electromagnetic excitation. I mean, after the production of gamma-gamma, the light-by-light scattering, we can take into account some emission of the photon from first or from second, or both from first and second nucleus. So we can calculate the excitation function. We have really very good agreement with the data, and we can calculate this one. And last slide, I would like to only show you that during 3-week summer student program, students have calculated the cross-section where the larger probability is in the case when 1 neutron is emitted from first nucleus and 1 neutron is emitted from second nucleus. It's about 2%, but we can estimate that the larger cross-section should be when 0 neutron is emitted from the nucleus, is 97%. Okay, it's all. Thank you very much.
So then I think we want to go straight into the question session. Thanks a lot, Mariola.
Thank you very much. Thank you.
Are there any questions on the talk? We can see your desktop now, just to let you know. Okay, any raised hands? Okay. So for this two-gluon exchange in the ultraperipheral collisions, right?
Yeah.
So that doesn't close yet the gap to the between the measurements and your calculations, right? So can you say a bit more about what you think could close the gap, or?
You mean the gap in the context of two-gluon exchange?
No, sorry. I mean, sorry, gap was probably a very, very stupid word. No, I mean, you see for all of the measurements, for the CMS measurement, for the Atlas measurement, for the new Atlas measurement, you see that the measured cross-sections are always quite a bit higher than your calculation. And you were discussing that you were to, so that you've now added the two-gluon exchange, but that there might be other things that you could add to close the difference between the data and the prediction. Can you say a bit more what this could be?
So we have only idea that this can be just two-gluon exchange on the pionic boxes, but we have no idea what can be additionally here. So we know, as I said, that we know that we are missing something, but it's really very difficult to say what it is.
Because for this, then you would want to see a bit more information in terms of differential cross-sections also.
Yeah.
Do you have any suggestions for differential cross-sections that could give you a better idea of what you would be looking for?
No, I'm sorry. It's very difficult to,
It's okay. It's okay. I mean, I don't know at all either. So this is why I ask. Okay. But I guess the two-gluon exchange in the pionic box would be also even a bit smaller than what you have now for the two-gluon exchange. Or would it be the same size?
Yeah.
No. Okay. So thanks a lot again.
Thank you very
for
much.
this night talk. And a lot of work has gone into this. So now...
Can I make a comment?
Sure. Yes,
I had raised my hand. So Mariola, this uncertainty, as you have explained, the photon flux goes into your calculations as an ingredient. So at what level do you believe that photon flux is accurate? Or in other words, can you calibrate? Do you foresee a possibility to somehow calibrate or cross-check your photon flux with another observable?
So sorry, can people hear Mariola?
Oh, sorry, I was unmuted.
Okay.
But I can explain. Okay, so I think that we would like to implement the most realistic situation, and I think that the realistic form factor is the most accurate. So when we implement the monopole form factor, so maybe this resolves the situation that then we can have the larger cross section. But I think that the answer is not here. Okay, so we know, for example, that the realistic form factor really very nicely describe the d-lepton production. So that's why we are sure that the realistic form factor is good way to describe, to use in the context of the equivalent photon approximation. So I have no idea about some different form factor.
Hello.
Okay.
I also raised the hand earlier.
Yes,
so just briefly, since you mentioned possible missing contributions like the pion loop or some others, what is the risk of double counting between these contributions and how do you want to deal with that?
A moment, maybe I will share again my presentation. Okay, so here we have the results where we include this double counting and without this one, and we see that different is about twice, but we know that we should take this lower line. But as I said, it's really very difficult just now answer on the question something more about the coherent sum of both process. We can predict that maybe this cross section should be a little larger, but it's very difficult to say what means a little larger. Okay, so maybe we can hope that these two gluon exchange or maybe pionic boxes, because we have no contribution for pionic boxes, so maybe this will help to describe the experimental data, but we have to check this one.
Okay, thanks.
Thank you. More questions?
Okay, there was a raised hand earlier from Chuchurek.
No, but I don't have any. This was not question. I wanted to say, but Mariola already answered to Rainer, but we calibrated cross section for leptons, and it works very nicely for leptons. Mariola did beautiful calculation for leptons, and but Mariola answered in the meantime, so I lowered my hand.
So that's why we believe in this form factor. Yeah.
I think my personal opinion on that issue from an experimental viewpoint would be the pseudoscalars eta prime, because supposedly there the cross section is very well known, right? I mean, so once there is an experimental signature of the eta or eta prime, I think that would be an independent check of your photon flux or the validity of the photon flux.
But for the ultra-peripheral collisions, yes?
Yeah, exactly.
Yeah, so maybe it's a good way. Okay, thank you.
Okay. Any more questions on these topics? Or also, because it's a general discussion, we can also still take questions to earlier presentations. Otherwise, yeah, if not, or yeah, maybe one question to connect this talk now to the earlier earlier discussions. You mentioned that you can also produce the heavy vector bosons, right? The WW, which we were talking about earlier in this session. Does your calculation also work for proton collisions, or is this completely separate?
You mean the context of light by light scattering also, yeah?
No, this is then when you go from the heavy ions to just protons.
Okay, so I'm not sure it was a question for me or the previous presentation, but I would like to only add that we have calculation for the proton-proton collisions for the light-by-light scattering, where we include the W boson.
Okay, I think that answers the question a bit. Then I think we are perfectly well in time for the coffee break. So this is scheduled to be 25 minutes, so everyone can go stretch a bit. Please feel free to come back to this room earlier, just to have a chat or whatever, get yourself a coffee, and we will reconvene at 5:20. Thanks a lot for this session.
Thank you very much.
Thank you. Thanks to all the presenters.
Thank you.
Thank you.
I just wanted to remind the forthcoming speakers, if everyone wants to try sharing their slides, this is the right time to do this. Otherwise, the waiting slide will be shared.
Right. Hello, everyone. We have 1 more minute, but I'm just testing my audio. And if possible, I would kindly ask the host of the meeting to add me as co-host.
I already did.
Thanks.
Yeah, no problem, Mirka.
Okay, perfect. Thank you. All right, so I see we have the first speaker connected. So we will have a session devoted to flavor violation, FCNC, top-quark mass measurements, and then top-quark properties at CMS. So let's start with Nicolas. Hopefully you can hear us. Please try to share your slides.
Yes, hello everyone. So hopefully you can see my slides now.
Yes, perfect.
Okay.
Thank you a lot.
Okay, so first of all, thanks to the organizers for giving me the possibility to give the talk today. So I will be talking about 2 different or 2 separate topics, but both will end up in the same final states in the detector. So the first one will be actually a measurement of flavor of lepton flavor universality, and the second one will be 2 searches for flavor changing neutral currents, and both in top-quark final states. So let's start with the first one, the measurement for lepton flavor universality. The standard model predicts us actually that all the charged leptons, so electron, muons, and taus, only differ in their mass. But under the electroweak force, in principle, everyone or all of the 3 should interact universality. So this is what we usually call lepton flavor universality. That means, in particular, that all the charged leptons of the different flavors have the same coupling strength to the W boson, so also the same probability to decay. So if we look actually at W boson decays, this has been already precisely measured at lab. So on the right-hand side, you can see a summary of the lab measurements where you see the different decays of the W into the different lepton flavors. And you see that for the decay into tau and neutrino, actually a deviation from the standard model expectation of 1 was observed. So this deviation was approximately 2 sigma. And the aim was now to remeasure or to measure a quantity which is similar, which is the ratio of the branching ratios of the W to tau to W to muon, with a precision of about 1 to 2%, because this would either prove this discrepancy which was measured at lab or fully rule it out. So the analysis strategy for this measurement is that we actually use TT bar final states and not only W boson production. The advantage of using TT bar final states is that you can use 1 top decay to actually trigger the event. So this is what we usually call a tag lepton, because if the W from 1 top goes into lepton and neutrino, we can use this to trigger the event. And then we know, since we have a TT bar final state, that we have a second W boson, which is not having any requirements in terms of kinematics. And we can use the lepton from the second W boson as a probe lepton on which we actually perform the measurement. So this means we can go as low in transverse momentum of the lepton we probe as our reconstruction works in the detector. And what we do is we only look for leptonic tau decays, because then we additionally profit from the fact that leptonic decays have a smaller reconstruction uncertainties compared to hadronic tau decays. So our main task is actually to distinguish between prompt muons from the W boson decay and from taus decaying into muons. And what we do is we have 2 main separating or discriminating variables. And those are the transverse, the absolute value of the transverse impact parameter, D0, and the transverse momentum of the muon PT. And this helps us to distinguish prompt muons, which usually have a narrower transverse impact parameter, from actually taus decaying into muons. And on top, the transverse momentum allows us to also distinguish between the third component, which is actually a background to our measurement, which are muons originating from hadron decays. So you can see actually now in these plots on the right-hand side that if you look at the 3 main components, which are prompt muons, then muons coming from taus and muons coming from hadron decays, that all of them are distinguished in the shape of both D0 and PT. Now, what is applied as the baseline selection in this analysis is that we have a standard TT bar dilepton selection. So we are looking for either electrons or muons as tag leptons and muons as probe leptons. Then we require to have 2 B-tag jets, and obviously the leptons need to be of opposite charge. And for the case where we have the dimuon channel, we obviously veto against C bosons. So that means our tag lepton is required to pass a trigger, and our probe lepton can go down to PT of 5 GeV, and we can probe the full PT range for our analysis. The remaining backgrounds, as you can see in the figures now on the right, which are for the dimuon channel, are the hadrons decaying into muons, which is shown in yellow, and also for the dimuon channel, the C boson plus 2 B-jet production, which is shown in the light blue color. Now, one word on the transverse impact parameter, D0, which is actually one of the 2 main discriminating variables in this analysis. So we define the transverse impact parameter as the distance of the closest approach of a muon track to the transverse plane. In our case, we define it with respect to the beamline instead of respect to the primary vertex, because this is more process independent. So what we do is that we actually take the shape of the D0 distributions from data, because it's not well modeled in Monte Carlo, and we determine this shape in 33 bins in PT of the muon and eta, absolute value of eta of the muon, and we determine it in a region where we are looking for C2 muon, C2 dimuon decays, and then from this region we subtract the remaining backgrounds which we take from Monte Carlo and use the shapes of this template in order to apply it in the signal region. Obviously, since we measure this in a dimuon selection of the C boson decay and not in a TT bar selection, we assign an additional systematic uncertainty due to this approach. And this is basically estimated by taking the ratio of the D0 distributions between TT bar and C2 mu, and then applying this ratio to rescale the data when we actually calculate our systematic uncertainties in the signal region. Now, coming to the main background. As I already said, the main background in this analysis is actually muons coming from B or C hadron decays. So if they decay, usually they accumulate at larger D0. So what we do to estimate this background, we estimate its normalization from data in a same sign control region, where we fully rely on the shape of the D0 distribution in the same sign region for Monte Carlo. So we just take the normalization, and in order to estimate remaining other backgrounds in this specific control region, for example, the dominating one is TTV production, we actually look at the high PT region of this same sign selection, as you can see in the bottom plot, and we use this high PT region to actually subtract the contribution from TTV, and afterwards we apply this normalization factor, which we obtain to the signal region. Obviously, we also account for modeling differences between same sign and opposite sign taking from Monte Carlo. And what you see is if this thing is applied, you have in general a very nice agreement of data Monte Carlo in those control regions. And also the uncertainties which we get, we take them from, let's say, 3 different sources. One is actually the statistics of the same sign control region. The second one is the Monte Carlo generator or the modeling in general, which we have in this region to estimate the different contributions. And also we vary this PT threshold in which we estimate the TTV contributions. The second background, which is only present in the dimuon channel, is C boson production with 2 additional B jets. So although we use the veto, we can still see a visible contribution of this background in our signal region, as you can see in the 2 plots here on the right-hand side. In order to estimate its normalization, we also use data. So what we do is we leave away the cut of the C veto, and then we fit the invariant mass distribution of the 2 muons between 50 and 140 GeV with a convolution of a Bright-Wigner and a Gauss for the C mu background, and also with a third order Chebyshev polynomial for the remaining backgrounds. And the normalization factor, which we obtain in this method, is approximately 1.4. And this is then applied to scale the C2 mu contribution in the signal region in the dimuon channel. We also use different fit functions in order to estimate a systematic uncertainty to estimate this background. Now coming to the statistical interpretation. So for both channels, so either we have an electron as a tag or muon as a tag, we perform a 2D profiled likelihood fit in two variables, namely the D0 and the PT. So you see that in total we have 3 PT bins and I think 8 D0 bins. So we have in total 24 bins per channel. So we have 48 bins in total in our fit. And the free floating parameters are the ratio of the branching ratios of W to tau and W to mu. And also we assign another parameter, which is free as a scaling factor for the top processes. So TT bar and TTV, because then we are not sensitive in our measurements to the cross sections of the top processes, which are dominant in this measurement. Okay, so the advantage of using actually this tag and probe method, which I told you in the beginning, is that many of the uncertainties in this measurement are correlated between the prompt muons and the muons coming from the taus. And so if we take a tag and probe method, they will cancel out in our measurements because we do this division of the ratio to taus and the ratio to muons. And also applying all the corrections and the scalings which we obtain from the data, we have an excellent data Monte Carlo agreement in all the signal region bins. So for illustration purposes, I show you one of those bins for the dimuon channel in the middle PT range. Coming to the systematic uncertainties. So the measurement is in principle dominated by systematic uncertainties. So you see in the table in the bottom that the data statistics are a bit smaller than the total sum of the systematic uncertainties. The leading systematic uncertainty is actually coming from the extrapolation uncertainty of the prompt D0 templates. You remember that we usually estimate this by comparing TT bar towards C2 mu decays. Then the second dominating one is the theoretical modeling uncertainty. So for example, parton shower or scale variations. And then the third one is the uncertainty which we get from the estimation of the hadron to muon background in our same sign region. In particular, the different Monte Carlo generators we use in our estimate are the ones which then propagate through in the systematic uncertainties. The last one, which is obvious in a measurement where you only look for muons, is the muon isolation requirement efficiency, and also for the low PT regime, the muon reconstruction efficiency uncertainty. Now coming to the result, you see in this plot on the right-hand side, all the previous results of the different ratios of branching ratios. And in the bottom, you see the result which we have now in this latest measurement from Atlas. You see that the measured value of the ratios between W's going to taus and W's going to muons is 0.992 plus minus 0.013, which means we are in perfect agreement with the standard model expectation of 1. And the second point is that we actually almost doubled the precision of the combined lab measurement, which you can also see in this plot, just the data point above the Atlas measurement. So this measurement of lepton flavor universality is actually the most precise measurement which we have today. Okay, now let's go to the second topic of the talk, which are measurements or searches actually for flavor changing neutral currents in TT bar decays. So as you know, flavor changing neutral currents are actually forbidden at tree level in the standard model. And also at higher orders, they are strongly suppressed by the JIM mechanism. However, there are several extensions of the standard model which actually allow flavor changing neutral currents, or at least increase the possible cross sections. Such are, for example, R-parity violating SUSY, or 2 Higgs doublet models, or composite Higgs models, or warped extra dimensions. So those all predict a significantly larger probability to observe those processes in LHC collisions. And I will present now 2 searches for such processes involving top quarks. So the first one is actually coupling or flavor changing neutral current between light quarks like up and charm and a top quark and a photon. So you see on the right hand side 2 possible Feynman diagrams. In the first one, actually the flavor changing neutral current comes into production. So you actually have a collision of a gluon and the light quark, and then you produce, sorry, the first one is the decay, the second one is the production. And so you produce in the first one a top quark and a photon coming from the light quark, and in the second one, you have a standard TT bar production where in the decay of 1 top quark, you get a photon and a light quark. So in both cases, the final signature in the detector is actually 1 photon and 1 top quark. So this analysis or this search only considers leptonic top quark decays, which means you require exactly 1 lepton, 1 photon, and BTEC one BTEC check with additional transverse missing energy from the neutrino. Both models with left-handed and right-handed couplings are considered, and in the end, a neural network is applied, which is trained on kinematic properties of the photon, the lepton, and jet, and the transverse missing energy. And separate trainings are performed for left-handed and right-handed couplings. So the dominating backgrounds in this analysis are coming from W plus gamma plus jet and C plus gamma plus jet production. They are both estimated from data in dedicated control region. So for the W, we actually require a non-BTEC jet, and also we require the invariant mass between lepton and photon to be outside of the C peak to suppress C plus jet production. Then for the C, we require 2 leptons of the same flavor and opposite charge, but no additional requirements on the jet or ET miss are made. Then also we estimate the number of electrons or hadrons which are misidentified as photons from data. So for electrons, we do it by just measuring the rate in C-boson decays, whereas for photons, we do it by just varying the photon selection criteria. The results of this analysis can be shown in the plot and in the table on the right. So if you perform a simultaneous binned profile likelihood fit to the neural network output, which you can see in the top plot, you see that no significant axis on the standard model expectation is observed. That means we can set limits on the effective coupling parameters of the theory, and they can also be translated into limits on the cross-section of and the branching ratios of these flavor-changing neutral current processes. So as I said, those are upper limits because no significant excess above standard model expectation was observed. Now coming to the second search. So here, actually the flavor-changing neutral current interaction comes in between the Higgs boson and the top and the light quark. So you see on the right-hand side, again, a TT bar production, but then instead of both tops decaying into B and W, one of them goes into a Higgs and a light quark. And this branching ratio to go into Higgs and light quark is actually largely enhanced by some beyond standard model scenarios inexplicitly if the light quark is a Chang quark. So in the end, in TT bar production, we expect again one standard top decay and one decay into Higgs plus light quark. And since the largest branching fraction of the Higgs boson itself goes into BB bar or tau or di-tau, we actually look for top plus light quark plus Higgs to BB or Higgs to tau tau final states, which means that in the end, this final state can also be combined with searches where the Higgs goes into 4 leptons or into gamma gamma in order to increase the sensitivity, but I won't cover this in this talk. So in this talk, the analysis is only looking for 1 lepton in case you have a BB final decay of the Higgs, or for 0 lepton in case you have a tau tau decay. Now let's start with the, also for both, it applies that TT bar obviously is the main background, but let's start with the BB bar decay of the Higgs. So for this, we estimate the multi-check background using a matrix method. And then we require to have at least 2 B-checks since we have a Higgs BB decay. And then we categorize the whole analysis into different bins of chat and B-chat multiplicities. In the end, a likelihood discriminant is used, which takes into account the 4 momentum vectors of all the chats, including B-tagging information. You can see this discriminant on the right-hand side for signal and background scenarios. Then, in the case where you have a Higgs tau tau decay, actually the fake tau background is estimated from data by just loosening the tau requirements and also flipping the charge of the tau to get an idea of the systematic for the tau reconstruction. And then in the end, a boosted decision tree is used, which we train on the invariant masses or combinations of the products of the PT of the leptons, or also momentum fractions of the leptons carried away by the visible decay products of the taus. Now coming to the results of this measurement. So also for both decays, Higgs to BB and Higgs to tau tau, we use a binned likelihood fit in the discriminating variables of the respective analysis. But in both cases, also no significant excess above standard model expectation was observed. That allowed us to set limits both on the branching fractions going to light quarks and light up and charm type quarks. And in addition, as I said already, the analysis result was combined with searches for 4 leptons or for Higgs to gamma gamma decays. And you can see on the right-hand side in the top row of each plot, the combined upper limit of the Atlas experiment for the branching ratios of tops going into Higgs and light quarks. And this brings me already to the summary. So I presented basically two different kind of analyses. The first one was a measurement of the ratio of branching ratios of a W to tau and to muon. There we observed a perfect agreement with the standard model expectation, and we improved the lab precision by almost a factor of 2. You can see it on the right again as a summary plot. And I showed you two searches for flavor changing neutral currents in top-quark final states, where we actually target a variety of beyond standard model models, and always a flavor changing neutral currents from a top-quark to a light quark involving either a photon or a Higgs boson was looked for. The key ingredient for those analyses is obviously the background suppression, because they are dominated by TT bar background. And in both cases, machine learning techniques were used to achieve this. And in both searches, unfortunately, also no sign for flavor changing neutral currents was observed. Yeah, thank you very much.
Perfect, thanks. Thanks for being almost on time. Questions, I'm looking at raised hands, which I should be able to see. So don't be shy, ask a question. Can be any question, any level question, student, postdoc, professor, whatever question. Nicolas is here for you to tell you about everything about FCNC and lepton universality. Yeah, I see Thomas. Go ahead.
Hi, Thomas here. Say at the higher energy upgrade of LHC, if you would to repeat this analysis for the FCNC search in top-quark final state, would this potential top distribution in the proton be a limiting factor for this study?
To my knowledge, not. I think we can increase the upper limits, but I don't think that we run into a limiting factor.
Okay. So the top distribution in the proton is still very small as compared to
yes,
what you measure.
Because those are really, let's say more or less tiny branching fractions we are looking for, and I think they are not dominating by the parton functions for the top.
Okay. Thank you.
Okay, thanks. Then I see Stergios, if I pronounce correctly. Go ahead.
Yes. Can you hear me?
Yes.
Okay. So yeah, first, thank you for a very nice talk. So I was interested basically in the search, in the measurement that you do. And I was interested to know if you're using any trigger for that, because I saw that you are going down to 5 GV PT.
Yeah, so that's the main idea of this analysis, is that we don't run into issues with the trigger. That's the reason why we use the TT bar final state, because as you can see in the Feynman graph here, having a TT bar final state, we have actually 2 W bosons to probe, which means we can trigger on the lepton of one of the two and then perform the measurement on the other of the two, which means the second lepton on which we actually perform the measurement is completely unbiased with respect to the trigger. And this is why this gives you a much better sensitivity than if you look in, for example, W plus chat production, where you only have one W and then you need to fulfill the trigger for this single W.
Okay, so you are using a single lepton trigger, or?
Exactly. So the measurement just requires to have one single lepton trigger, and then due to the fact that you apply 2 BTEC chats and a second lepton, which is not fulfilling the trigger, but there is just a second lepton, you know that you are now in a very pure TT bar final state. And this gives us the sensitivity. This is the main factor of this analysis.
Yeah, thank you.
Thank you. I'm looking again. I had a similar question whether there is some trigger bias, but that just got answered. Maybe a little question whether there is some difference in the kinematics of the events when tau is produced. Of course, I guess half GV would be carried away by the neutrinos, but well, we do measure small scale properties of top, like the top width, which is 1 GeV, or the other of 1 GeV. So is there a possibility that actually the tau events are shifting the kinematics a little bit?
I mean, this is actually more or less what we use, right? Because if you look at the sketch, if you look at this sketch, we actually expect that a prompt muon will have, for example, a different transverse momentum distribution compared to a tau decaying into a muon. And this is actually also what we see in principle, because if you look at Monte Carlo, you see in the light green the prompt muons, which are in the bottom plot, in the PT plot, which have a very different shape of the PT distribution in the simulation, of course, compared to the leptonic tau decay. And this is actually why we use also the PT as a second variable in our fit in the end to distinguish the two processes. So let's say it's a main ingredient of the analysis that the tau decay into a muon has a different kinematic property in the end.
Thanks. I was looking too much just at the D0 plus. Okay. Any other question?
Hi, this is Aram. Can I ask a quick question on slide 4? I mean, this is a really, really nice result. Sorry, I meant slide 5. I was curious a little bit about so you say that you take the shape of the impact parameter distribution in this in data using the ZMMU selection, and and it seems like this is let's say the dominant, the largest systematic uncertainty. I was wondering if you could tell us a little bit more what exactly goes into this extrapolation uncertainty. Mainly, I'm wondering if there is also some statistical component to it from these control regions that can possibly be improved, let's say, with more data.
Yeah, so the main idea for the systematic uncertainty is actually really, since we measure the shapes in a CMMU selection in data, and then we apply it in the end in a TT bar final state, we just compare the, let's say, data Monte Carlo comparability between the D0 in TT bar final states and CMMU final states, and we just take the difference of this ratio and apply it to scale when we go into the variations of the systematics. So this is the main idea is just, since we measure in a different process than we actually have in our signal region, we also compare the two and assign it as a systematic. So the statistics, I think, it's a very small, let's say, ingredient for this, because both in the TT bar final state and in the CMMU final state, if you use the full LHC run2 dataset, you have such a high amount of statistics that there is basically no statistical component in this comparison. So the real comparison really comes from the fact that the two different processes have let's say, slightly different environment, so different number of jets and so on, different kinematics, and this then translates through in your systematic uncertainty. So we are really not limited by statistics in both processes, TT bar and CMMU.
Okay, thank you.
All right, thanks a lot. So I think we should be closing the discussion, but I was checking whether we have some other hand raised. If not, then still people can please keep asking questions. You can ask in Zoom chat. The best place would be the Mattermost chat, and then these questions can be discussed at today's topical session, which is devoted to top properties and EFT. So please do not keep your questions secret. Thank you a lot to Nicolas for this nice talk. And we move on to top-quark mass results by Atlas to be presented by Serena. Serena, are you connected? And can you please share your slides?
Yes. Can you? Yeah, I try to share the slides.
Yeah, we can hear you.
Okay.
We can see your slides if you can just maximize them, and that will be just perfect.
Okay, I think now you're able to see them full screen.
Right. Thanks.
Okay. Thanks. So good afternoon. I will present the recent measurement of the top-quark mass using the Atlas detector at the LHC on behalf of the Atlas collaboration. And just a brief introduction about the physics motivation on why it's important to study the physics of the top-quark. We know that the top quark is the heaviest elementary particle known until now, and its large mass is a fundamental parameter in the Standard Model, also because it has the highest coupling to the Higgs boson, and also due to the very short lifetime, the top quark decays before hadronizing, and this gives a unique opportunity to study the properties of a pair quark. Also, the Large Hadron Collider is the right place where to study the top quark properties, because it is a top quark factory and it has a very large pair production cross-section, as we can see in the plots in the bottom part of the slide, where the inclusive TT-bar cross-section is reported as a function of the center of mass energy, and we can see that the cross-section increases with the increasing of the center of mass energy. A fundamental parameter of the Standard Model is the mass of the top quark. This because it is important for electroweak precision tests, and also it played an important role to constrain the mass of the Higgs boson even before it was discovered at the LHC. And also it is important for the stability of the Standard Model vacuum. In fact, the measured value of the Higgs boson mass and of the top mass place the Standard Model vacuum at the border between the stability and the metastability, as we can see in the plots in the bottom part of the slide, which is the diagram stability phase plot. And it's really important to reduce the uncertainty related to the top mass, because this helps to discriminate between the metastability and stability phase. So there are different methods used to measure the top quark mass. The first method is that I report here is the direct measurement of the top mass, which means that the mass is extracted from the kinematic reconstruction of the invariant mass of the top quark decay products, and this is the so-called standard method. And in this case, data are compared to the Monte Carlo simulation that have different values of the top mass as input values. And this kind of measurement rely on jets and parton shower, and in general is a still controversial argument because of the definition of the mass itself. And then there is also the indirect measurement of the top mass, which is done by using cross-section measurement, both inclusive and differential, and this is the so-called pole mass. And in general, there is a difference of the order of 1 GeV between the Monte Carlo mass, which is the direct one, and the top pole mass. So the first measurement that I will show is the measurement of the top pole mass using the TT-bar plus 1 jet production. This is an indirect measurement of the top pole mass obtained by extracting the value of the mass from the differential cross-section measurement of the TT-bar plus 1 jet production. And for this measurement, the data collected by the ADAS detector at ATV or PP collision have been used, and this data correspond to an integrated luminosity of 20.2 inverse femtobarn. For this measurement, instead of using the cross-section of the TT-bar system, the cross-section of the TT-bar plus 1 jet system has been used because it is more sensitive to the mass of the top. And just a brief description of the method used to extract this mass. Basically, one normalized differential cross-section is measured as a function of the invariant mass of the TT-bar plus 1 jet system, and then the unfolded distribution at parton level is compared to the next two leading order plus parton shower TT-bar plus jet calculations. The observable that has been used for this measurement is reported here below, is this R observable, which is exactly the normalized cross-section as a function of the rho S variable, and the rho S variable reported here below on the right is defined as the inverse of the invariant mass of the TT-bar plus 1 jet system. So about the event selection and reconstruction in this measurement, we ask for exactly one reconstructed electron or muon, at least 5 jets, and then we ask for an extra jet that characterizes the TT bar plus 1 jet system, and this is the leading jet with PT greater than 500 GeV, and this jet is not used in the reconstruction of the TT bar system itself. You can see below the event yields of this measurement for both the electron plus jet channel and the muon plus jet channel. And there is a very good signal purity of 94% for the electron plus jet channel and 95% for the muon plus jet channel. And this is reflected in the plot reported here in the slide, where the comparison between the data and Monte Carlo is reported, and there is a very good agreement between data and Monte Carlo. So, as I said, this measurement has been done by using an unfolded distribution at parton level. The normalized unfolded distribution is reported here in the plot on the right as a function of the rho s variable. And you can see in the plot the comparison between the data and the different Monte Carlo prediction at next to leading order plus parton shower, and these different predictions have different pole mass value as input. And you can see from the regio plot that the best fit is obtained by the prediction that has the top pole mass equal to 171.1 GeV. To obtain the value of the pole mass, the least square method is used, and the formula is reported here below in the slide. And the value of the pole mass is the one that where the fit minimizes this chi-square calculation. In this measurement, both the pole mass and the running mass have been measured, and in the table here on the left, you can see the systematic uncertainty that affect both these measurements. And in general, the dominant uncertainties come from the shower and hadronization for the modeling, as well as color reconnection. And concerning the detector response uncertainty, the leading one is coming from the jet energy scale. And then for the theory uncertainty, the leading uncertainty is the scale variation. It's important to notice here that the scale variation uncertainty is actually higher for the mass, for the running mass with respect to the same uncertainty, but on the top one mass. And below here, you can see the extracted value of both the pole mass and the running mass. And these two mass are compatible between each other if we translate the running mass to the top pole mass by using the QCD relation between them. So in summary, the ATLAS detector, as well as also the CMS collaboration and Zero, have measured different, the top pole mass in different analyses, and you can see the latest results of these collaborations reported here in the plot on the left, and the value that has been extracted from the measurement that I just presented is reported in the plot in red, and is compatible with the values obtained by the other collaboration and also by ATLAS in other channels. And another thing that is important to notice from this plot is that the same measurement has been done also at 7 TeV, and it is the value is reported in the plot is the second from the bottom. And if you compare the two values, you can see that in the measurement at 8 TeV there was a reduction of the uncertainty of a factor 2 with respect to the one obtained at 7 TeV. There is also in the ATLAS collaboration a recent measurement of the top pole mass at 13 TeV extracted using differential cross-section in the lepton channel, but this is not covered in this talk. It was covered yesterday by Chang and Co. So moving to another measurement, I will present the results of the analysis where the top quark mass is measured using a leptonic invariant mass with It has been measured by the ADRAS collaboration at 13 TeV of PP collisions. It is a direct measurement of the top mass in the lepton plus jet channel, and it has been done with an experimental technique that uses semi-leptonic decays of the p hadrons that is produced in the top chain, decay chain. So the difference with the standard method is that in the standard direct method, the invariant mass of the lepton and of the P is used to extract the top mass, while in this experimental method, it's not used the B, but it is used the semi-leptonic decay of the B hadron. So at the end, as variable, it is used the invariant mass between the lepton and the muon, that is the product of the B hadron. And one of the advantages of this measurement is that it is purely leptonic, and this means that it's less sensitive to the jet's uncertainty. There was a proof of concept for this analysis by CDF, and also a similar idea was used by CMS to perform a similar analysis that was published recently. So in this measurement, we asked for exactly one isolated electron or muon. There is a cut on the ATMs and on the mass of the W. We asked for at least 4 jets, at least 1 big jet, and at least 1 soft muon tagged jet. And from the soft muon, which means that basically we ask for a muon that has to have a PT greater than 8 GeV. You can see in the table in the bottom left part of the slide the event yield for both the opposite sign and same sign selections, and for both the selections we have a very good signal purity of 86%. And this can be observed in the plots reported here in the bottom right part of the slide, where the data, the ratio between data and Monte Carlo is reported for the mass of the W on the left and for the PT of the soft muon on the right. And also in both plots there is a good agreement between that and prediction. So the mass extraction in this measurement is done by using a profiled Binet likelihood template fit, and this fit is done in the region between 15 and 80 GeV of the invariant mass of the lepton and the soft muon. And this profiled Binet likelihood include all the systematic uncertainty as nuisance parameters. You can see here in the plot the sensitivity of this variable, the mass of the lepton and the muon. So the sensitivity of this variable to the different values of the top mass that are reported in the plots as blue, black, and red lines. And on the left, the plot is obtained for the opposite sign selection, while on the right part of the slide is for the same sign selection. And you can see that the plot for the opposite sign selection has a higher sensitivity to the mass of the top. The ranking plot of the nuisance parameter and their impact on the mass of the top is reported in this slide. So the pre-fit impact on the mass as well as the post-fit impact on the mass is reported, and the leading 4 ranked nuisance parameter that contribute to the impact of the mass are these 4, the first 4 in the plot. And here in this slide, you can see the systematic uncertainties that are grouped, and the dominant uncertainties on the measurement come from the modeling, in particular from the initial state QCD radiation, from the big quark fragmentation, and from the EV flavor hadron decay modeling, while concerning the detector uncertainties, the leading one is due to the pileup reweighting. So the results of the measurement is reported here on the left, where we can see the best fit of the top mass, and the blue curve corresponds to the statistical plus systematic uncertainty, while the red dotted line is the statistical only uncertainty, and the results of the fit is reported here below, where you can see the value of the mass of the top, which gives a very precise measurement of the top mass and is really competitive with the standard direct techniques. And this can be observed from the plot on the right, where the values of the standard techniques obtained by the Atlas collaboration in different channels are reported, and the value that is obtained with this experimental technique is really compatible with what is shown in the plot here. So in conclusion, the mass of the top is a key parameter in the standard model and beyond standard model physics, and it is known with high precision. It is investigated with different approaches. So as I said, there is an indirect measurement of the top mass that can be performed by using cross-section measurement, both differential and inclusive, and also several direct measurement of the top quark mass by using the kinematic of the decay products of the top. And what I show today is this experimental technique that use semi-leptonic decays of the hadrons and gives a very good and precise results of the top mass. So all those methods provide a very precise measurement of the top quark mass, which are compatible with the previous results of both Atlas CMS and D0 collaboration. Thanks for the attention.
Thank you. Thanks very much for these nice standard and non-standard top mass measurement methods. And everyone is invited to raise hand and ask a question. Looking at the list. If I happen not to see the raise hand, just go ahead. Yeah, we have a question. Go ahead. I'm not sure about the name though.
Yeah, I'm Najia. Hi, Jiri. So I have a question. I think it is in the slide for TT1 plus jet, TT1 plus jet, plus one jet, where you compare the running and the pole mass.
Yeah, I think.
Yeah, exactly. So you mentioned that the scale uncertainty is larger for the running mass, right?
Yeah.
Could you explain why is that so?
So basically, it should be due to the to the scale variation factors, because probably for the running mass, the region near the threshold of the TT bar plus jet production is more sensitive to this scale variation.
You mean the value that the scale has changed is different between the two, or like,
yeah.
Okay. Okay.
Yeah, this is my understanding. So yeah.
All right. Thank you. Any other questions? Looking again. So meanwhile, I'd have just a simple question, maybe slide 15 on the profiled systematic. So I was just curious to what extent the branching ratio shifts affect the overall normalization, and to what extent they affect kinematics like the PT of the soft muon.
So, sorry, can you repeat the question?
Yeah, so there are various BR functions that are varied, and my question was to what extent they affect the overall normalization of events with the soft muon tag, or to what extent they also have effect on PT of the muon.
Honestly, I don't know.
Okay, no problem.
So, Jiri, are you asking about a direct effect or an indirect effect? Are you asking whether these branching ratios change the shape of the PT of the muon, or they're just a normalization effect? Is that?
Yeah, that's my question.
So this I think it's predominantly a normalization effect. I mean, it's predominantly a number of events effect. There's also PT effect, but if you take, for instance, Herwig and Pythia, you will see that the PT of the muon is somewhat slightly different. When you change here you're just changing the number of events that provide you with a certain decay. Then the way the whole fragmentation and consequently the evolution of the kinematic is independent of that. So it's taken systematically over by either PT or Herwig, and so that is affected by other systematic uncertainties.
Okay, thank you. More questions? Again, if you are shy to ask, then use Mattermost chat. We have some discussion on the Electroweak topics, but top questions should be there too. Right. So thanks again, Serena, for this nice talk. And we move on to CMS results on top properties, if I'm correct, by Giulia.
Hi, yes.
Right, we can hear you.
Yeah, yes, maybe I can also.
Yeah, we can also see you, and please try to share your slides if possible.
Okay. Okay. Let me know if you can see them.
Yeah.
Okay.
All set up, go ahead.
Okay. Okay, so I will present recent measurements of the top quark properties in CMS, focusing on a selection of results. The top quark is the heaviest elementary particle discovered so far, with an extremely short lifetime, which allows us to observe the properties of the bare quark, and with a large Yukawa coupling to the Higgs boson, which makes it an important element in the understanding of the electroweak symmetry breaking. Then it is also an ideal candidate for spin measurements, since the information of the spin is preserved in the angular distribution of its decay products. And thus, studying the properties of the top quark is very important to test the consistency of the standard model and to search for new physics phenomena beyond the standard model. For the spin correlation, we measure the full spin density production matrix in the dilepton channel. First of all, we perform a direct measurement which requires the full reconstruction of the TT-bar system, measuring angular distribution in the TT-bar as frame using an orthonormal basis. The double differential cross-section are parameterized by polarization and spin correlation coefficients, which are individually probed using one-dimension angular distribution. Here I show the distribution of the opening angle between the two leptons, which has a maximal sensitivity to the alignment of the spins of the top quark and is the most precise observable. The data unfolded to the proton level are compared to different predictions in the right plot. Then we can also perform indirect measurement using observables in the laboratory frame, like the angular distribution of the charged leptons and the angle between the leptons in the transverse plane, delta phi, which is very precise experimentally, thanks to the excellent resolution of the lepton angles. Then from the spin correlation coefficient summary, we see that all the distributions are in close agreement with the standard model prediction. And then we use the unfolded results to constrain anomalous coupling like the chromomagnetic and the chromoelectric dipole moment shown here on the top. But from this, we observe no new physics because all the results agree with the standard model. Then the delta phi distribution is particularly interesting because both in Atlas and CMS, it's shown a tension between the data and the prediction. So now within the LAC top working group, we started an Atlas and CMS comparison, which is the first at 13 TV, using normalized cross-section at parton level. The Atlas and CMS data show a very good agreement, and also the agreement is also very good between the two main Monte Carlo prediction of the two experiments, which was never seen before. The agreement with the next to linear order calculation is quite good, but not great yet. And we also compare the data to further Monte Carlo prediction, where in particular the CMS map graph plus PTA8 and 2 additional jets looks very promising. Then the polarization fraction of the W boson are determined by the structure of the TW vertex and follow the unitarity constraint in the standard model. So prediction of the standard model can be tested with high precision measurement of this polarization, while instead we can probe new potential physics processes that can change the probability of the WLCT states, searching for anomalous contribution to the TW vertex, to TWB vertex. In particular, we measure the polarization fraction using the distribution of the cos theta star, where theta star is the polarization angle between the direction of the charged lepton and the one of the B quark reversed in the W boson rest frame. And this fraction corresponds in the standard model to the 70% for the longitudinal one, to the 30% for the left-handed one, and to 0% for the right-handed fraction. To improve the experimental precision, an Atlas and CMS combination has been performed using the round 1 data at ATV, in particular using the lepton plus jet channel in Atlas and the electron or muon plus jet channel in CMS together with the single top T channel. And the results for each of the fractions are reported here for each measurement. Then here I report the results from the combination, and we can see that they are in agreement with the standard model at a next to linear order in perturbative QCD. And in particular, the precision on the left-handed fraction is around 3.5%, and on the longitudinal fraction is around 2%, giving an improvement with respect to the most precise single measurement of around 29% and 25% respectively. Then we also set limits on the TWB anomalous couplings, in particular on the right-handed vector and on the left-handed and right-handed tensor coupling, which are supposed to be 0 in standard model. And here you have the resulting plot and also the allowed regions at a 95% confidence level. Then to extract the top Yukawa coupling, we exploited the effects of the weak correction that are due to a virtual exchange of a vector or a scalar boson gamma between the two top quark that affect the cross-section only at an order of alpha strong square or alpha weak. So the contribution to the inclusive TT-bar cross-section is small, but this may lead to large distortion of the TT-bar differential distribution near the production threshold region. In particular, if we consider the Higgs boson as for the virtual exchange, this will depend on the top X Yukawa coupling, and the cross-section will have a quadratic dependence on it. To take in consideration this correction, we then generate differential cross-section for different values of YT, which is the ratio between the top X Yukawa coupling with respect to its standard model value, as a function of two variables: the invariant mass of the TT bar, shown on the left, and the delta rapidity of TT bar, shown on the right, where we can see that the most sensitive region to the correction is at low invariant mass and a small rapidity. Then we applied this derived correction to the gen level TT bar events in order to compare them to the data. So we have a new analysis using 4 and 2 data in the that constrain the top Yukawa coupling in the dilepton channel. And even if we use a partial kinematic reconstruction, we can achieve an improved sensitivity using two proxy variables, which are the invariant mass of the two big quarks and the two leptons, and the difference in rapidity between the two pairs of big quark and leptons. Then we generate differential cross-section for different coupling values as a function of these two variables. And then to constrain the coupling, we perform a two-dimensional likelihood fit in bins of these two variables. And in particular, we extrapolate in each bin the expected yield as a function of the coupling with a quadratic fit that has the same order of the weak corrections. Then we also had another analysis using 2016 data, which was the first to measure the Yukawa coupling in TT bar events. And for this analysis, we consider lepton plus jet channel, and we use a full kinematic reconstruction. In particular, here was also introduced a new technique for events with one missing jet, which enhanced the experimental sensitivity in the low invariant mass region. In this case, to constrain the coupling, we use a two-dimensional likelihood fit in bins of the TT bar invariant mass of the delta rapidity of TT bar. Then after the fit, we can extract upper limit on the top quark Yukawa coupling, scanning the likelihood as a function of the coupling. So here you have the results on the left for the lepton plus jet channel and on the right for the dilepton channel. The results of these two analyses are in good agreement, and the one in the dilepton channel has a slight increase in the sensitivity. So the sensitivity is very good because it is also better than the one achieved from the four-top production measurements, but is a bit less sensitive than the X combination. However, this is a model-dependent measurement, while this is model-independent. Then moving to the measurement of the mass of the top quark, here we measure the mass of boosted quark decaying hadronically in the lepton plus jet channel, where the products of the hadron decay are reconstructed as a single jet. Here, a new jet reconstruction technique called XCON was used for the first time, and this consists in a clustering clustering two steps procedure, where first of all we find two jets at large radius and with a PT above 400 GeV, and then for each of the jets we find three subjets with a PT above 30 GeV that are then combined to reconstruct the final jet. This method gives an excellent resolution of on the jet mass, and then we can extract the mass of the top from normalized TT bar cross-section as a function of the mass of the jet unfolded at particle level. The results are reported here with their uncertainties, and the precision of this measurement, that is around 0.7%, even if it's not the most accurate, is, I would say, pretty amazing, given that we are in a boosted topology. Then we can measure the mass of the top quark from multi-differential distribution. In particular, here we consider normalized three-dimensional cross-section as a function of the invariant mass of TT bar, of the rapidity of TT bar, and of the number of extra jets in the lepton channel. So these cross-sections are compared to next to linear order prediction with different PDFs to extract the values of the alpha strong and the top mass in the pole scheme. Then we can also perform a simultaneous fit of PDF, alpha strong, and mass top and next to leading order, and we add the deep inelastic scattering data from here to achieve very precise measurement. In particular, the one on the top mass, which has a precision below 0.5%, is the most precise one got from a single analysis. Then we also study the impact on the PDFs, which is particularly significant on the gluon PDF at large values of X. Then here we measure the mass of the top from an inclusive cross-section measurement in the IMU channel, where we perform a simultaneous fit of the TT bar cross-section and of the Monte Carlo top mass to extract the values of the alpha strong as a function of as a scale of the Z mass, a top mass in the minimal subtraction renormalization scheme, and of the top mass in the pole mass scheme. The values for the different PDS are shown in the table. Then for the first time, we measured the running of the top mass, which is extracted by differential cross-section measure as a function of the invariant mass of TT bar in the IMU channel, compared to next to leading order prediction calculated for different values of masses, of top masses. We then perform a maximum likelihood fit to multi-differential distribution in order to do a simultaneous measurement of the differential cross-section as a function of invariant mass and of the Monte Carlo top mass. The values are calculated for a scale for each bin in the MTT bar distribution. And we can see that the running that we observed is in agreement with the prediction of the corresponding renormalization group equation within 1.1 sigma. Also, we exclude a no-running scenario at above 95% confidence limit. Then to extract the top CKM matrix elements, we perform for the first time a direct model-independent measurement in the single top T-channel events. In particular, we consider processes that are directly sensitive to the different matrix elements and both the production and the decay vertices of the top quark. So in particular, we consider three signals: the STBB1, where we have the VTB element, both the production and the decay vertex of the top quark; the STBQ signal, where we have the VTB element at the production and the VTQ element at the decay vertex; and the STQB signal, where we have the VTQ element at the production and the VTB1 at the decay. Then we define three categories with different jets, so 2 or 3 jets, and different beta jets, so 1 or 2, which are enriched in different signal and background processes. And then to separate this signal and background, we train for each of these categories ability discriminant that is then used in a simultaneous fit to the 3 event categories to discriminate between the 3 signals.
Just it would be nice to wrap up a little bit your talk.
Yeah, sorry.
Then
these matrix elements are extracted by signal strengths that are given by the measure T-channel cross-section times Bransfield ratio compared to their respective values. And assuming the CKM unitarity in the standard model, we get this limit at a 95% confidence level. Then we also investigate 2 beyond the standard model scenarios, one with additional quark families with a mass above the mass of the top and no CKM unitarity, and the other with additional undetected decays. All these results are consistent with each other, and these are also giving the best determination from the latest measurements in run 2. Then coming to the top forward-backward asymmetry, the symmetry in the TT bar production is due to next to linear order terms between the Cook bar initial states, and we search for anomalies in the angular distribution of a TT bar, in particular considering the cos theta star or C star distribution, where theta star is the production angle of the top quark relative to the direction of the initial state parton. In particular, we use the anti-symmetric function to measure the forward-backward asymmetry, approximated by the linearized variable AFP1, while the symmetric function is used to measure the anomalous electric and chromomagnetic dipole moments. In this measurement, we consider lepton plus jet events with boosted and resolved topology, and for each of these topology and for other categories, we perform a multi-dimensional template fit to 3 variables: the C star, shown here, the entity bar, and the XF distribution, where we can separate the Cuckoo bar process from the QG and GG ones. And then finally, we use a linear combination of 3D templates in a simultaneous fit to the observed differential cross-section to extract the values of FB1, the chromomagnetic and the chromoelectric dipole moments, whose values are consistent with the standard model expectation and also in agreement with previous measurements. Then in summary, I presented a lot of top-quark properties analysis with new run-to data and also with new channels and techniques. Few of them were probed for the first time, and there are also interesting combination or just comparison for the moment between Atlas and CMS. The huge number of produced top-quark events allows an increased precision of these measurements, which gives a better understanding of the top-quark properties and can constrain the new physics. And also now a lot of work is ongoing for results with new full run-to data, and so you will see them soon. Okay.
Perfect. Thanks a lot. Congratulations to this very nice and large set of results from CMS, including mass measurements. And I'm sure there should be many questions or to cover all the topics. So go ahead, raise your hands. Yeah, Lisa?
Thank you very much indeed for a lot of interesting measurement. I have a couple of questions on the Yukawa coupling measurement. The Yukawa coupling is extracted from the fit. I would rather look at the lepton channel, the recent one. The fit to MLB with a very large range. In fact, it's the mass of 2 Bs and 2 Ls. What I know for sure that MLB, when you have a mass of B and a lepton, at high values MLB is sensitive to off-shell effects. Is it in the list of uncertainties? I mean, I don't know exactly that MBBLL is sensitive, but naively, I would think that it should be sensitive too, despite the fact that you have 2 Bs and 2 Ls. Well, I guess Thomas Jesso was connected at least. He knows everything about it. So I would expect off-shell effects in the tail to matter in this last beam.
Yeah, I'm not entirely sure the uncertainties was considered, so I can maybe double check this.
Okay, thank you. And another question is actually, I saw the prefit plot, which shows significant, very significant slopes at the level of 20% from the first beam to the last beam throughout this distribution. What uncertainty covers this slope so that after the fit, the agreement is perfect?
Well, I think that here the most, I mean, wait, because I think the dominant uncertainties were due to the jet reconstruction and also to the also electroweak correction that were implemented, and then to the scale variation, so to the renormalization, factorization, and to the initial state and final state one. So probably thanks to that, after the fit, the agreement is quite good.
Okay, thank you.
Right, thanks. Then I think Philip was next to ask.
Hi, this is very impressive amount of work. And one of the questions that I was wanted to ask was regarding the spin correlation in the d phi LL. And I was just curious whether if the theory community had explanations for this, or whether, and so I had 2 questions, I guess. So the one thing is, if I recall correctly, this variable was used for stop searches.
Yeah.
And I wanted to know whether the access direction and whether the correlation direction is in the preference of the stop quark, or I can't remember which way the delta phi was changing. So that was one question. And the second question is whether the theory community had explanation in general for this.
Well, I know that there are calculation ongoing in the theory community to explain on this discrepancy between datum prediction. And I mean, for example, in the last open LAC top working group meeting, I think there were a presentation on that. And about your question on the top-quark, I mean, the combination we want to do for this spin correlation, in particular now on the delta phi distribution, is mostly just focusing on the 13 TV combination between the two measurements, the standard measurements. So for the moment, I don't think we are planning to do it for the stop measurement. But I mean, I know that in CMS we are going to have a result soon, I hope. And so maybe we can also compare that to the Atlas one.
Okay, but is the direction at least in an exciting way, or is it the direction the other way around? I can't remember
it's
whether
the other way around. It's not this anti-exciting way. No.
Oh, I see. Okay, thank you. That I was curious.
All right, thanks. I think Tomasz is next.
Hi, Tomasz speaking here. I would go back to this Yukawa top measurement, and I thank Lisa for bringing up the issue of offshore effects in the high tail of the MBL distribution. But I would also be curious to see, if you go back to the previous slide, actually, where you show the invariant, yes, this MTT generator. I mean, the variations there seem to be at the level of a few percent. Yes. And I would also be worried about the single top contribution in this particular case, because the single top TW associated production, or even the offshore effect, can integrate the rate below the threshold. So I'm wondering whether this region is really that well theoretically understood. I mean, there are all kinds of other effects in your threshold as well. So I mean, it's not really a question. It's just to comment.
Yeah, I think we can talk about that indeed.
Thank you.
Yeah, thanks for the comments.
All right, then maybe I can afford a question on slide 11 on the boosted mass. So I understand there is a novel technique that has an excellent jet resolution, but do depend on the description of the substructure modeling, or what is the main systematics? Whether this affects you, and what is the major systematics in this measurement?
Well, I mean, for this new reconstructed technique, let's say, we also consider an additional systematic. But yeah, the dominant one is still the jet mass scale, I think. So yeah, indeed, is still the most dominant one.
All right, thank you.
I think it was improved, I don't remember, as a factor of 2 or 3 before, since the previous measurement using this technique. So it's quite a good result.
Okay, I see Nida having her hand
Yeah, I
raised.
just wanted to comment on the previous question for the near threshold effects. There actually we have been in close contact with theorists like Michelangelo to include also possible uncertainties that are coming from electroweak corrections in that region, because this measurement is all about the extra electroweak effects, right? So that has been included in the measurement. But if there are other concerns, or I mean, there are clear recipe on how to deal with extra possible uncertainties and unknowns, we would be happy to know about that.
All right, thanks. No hand raised anymore for this talk, I assume, but we are entering the general discussion devoted to all the talks that we have had in this session. So any discussion point on lepton universality, FCNC, top mass and other properties. Yeah, no problem.
So, hello, do you hear me?
Yes, go ahead.
Yes.
Sorry, I wasn't sure. In relation to the top forward backward asymmetry, Giulia, so this is from my standpoint, this seems a really challenging measurement, right? Because we know that you're trying to look at quark instead of gluon, and gluon dominates, so you go for quark. You have limits and uncertainty. What is the the dominant systematic uncertainty here? Because I mean, if I look at slide 17, I see it's overwhelmingly gluon. And then you have quark someplace. But the knowledge of the templates, that's the question I'm driving at. How well known these templates are, how easy it is to separate these samples to begin with. What theory uncertainties were included? I mean, I'm assuming you have the usual modeling uncertainties.
Yeah, yes, we have the usual one, and yeah, I think we also consider additional uncertainties. I mean, due to these templates effect, but yeah, I don't remember if they are really dominant. Actually, I don't think so.
So if I may interrupt, indeed, okay, this is the precision of this measurement speaks for itself, right? The thing is that indeed the contribution for QQ is rather small, and isolating those things is challenging, and that's why I mean we went through this perturbative approach. But I mean all usual uncertainties are considered. And the differences between templates as well. But then, I mean, the differences that we see here, I mean, they are all reflected in the precision that we could have achieved, right? Which is not super precise if you compare with for example, charge asymmetry.
Yes, yeah, I have. That's clear, Nadia. I mean, dominated by statistical in some cases, and stat is as big as syst or even larger. So it's clearly a challenging effort. I was curious about whether there was, any particular feature, additional uncertainty in this specific case, because the template is so, the effect is so small.
The only particular thing that can contribute here is the relative contribution of QQ and gluon, which is considered. But apart from that, I mean, this contains the usual systematics.
All right, thanks.
All right, thanks for all these discussion. Any other question to any of the speakers?
Well, it's not a question. It's my preference would be if all the fits are supported by the plots showing the ranking of uncertainties of 10 highest uncertainties. Then it's clear what matters and what not when we measure Yukawa coupling, when we measure forward-backward asymmetry, something like that. And then there is no questions. It immediately answers what is important for the measurement. Atlas tries to do it. Well, actually, not even tries, always does it. Recently, at least. And it would be nice to see similar things from CMS.
Thank you very much for the very useful suggestion, Lisa. Indeed, I mean, we have sometimes only maybe very few cases that we provide the plot, but what we provide usually is a written statement on what is the most important and what is the size. Which is in the paper, but indeed, I mean, a plot can speak it more
especially showing pools. You know, the problem is that if you have data Monte Carlo disagreement before the fit, something has to correct for it. The question is it Yukawa coupling that correct for it, or is it something else? And if I fix Yukawa coupling to some value, something else will correct the distribution such that for any Yukawa coupling value, it will perfectly agree with data or not. Because it's such a subtle effect, that's why it would be really, really convincing. And it's a very impressive measurement. I would like it to be done by Atlas, but I would really appreciate more information.
Right. I mean, we should just make the information that, I mean, we should find a way to make the information that we have public, because, I mean, indeed, what you said, I mean, these checks are all done, right? And it is documented what is internally, what is pulling the uncertainty, I mean, which uncertainty is pulled and so on. But the only thing is that probably we need to think of a way to make those information public as additional material or something. In particular, if Atlas is going to do that, I think that would be very useful.
Well, if you check all recent Atlas results, at least 5, 6, whatever we published this year or last year, they all have this information.
Yeah, no, I meant about the Yukawa measurement. I meant
yes, of course, of course, because I'm pretty sure we will see similar mismodeling, because mismodeling doesn't come from JET for sure. I'm pretty sure it comes from top modeling, and that's why I would like to know how this works in CMS. And thanks a lot for providing this as auxiliary material, as in whatever shape, in whatever format you find appropriate. Thank you.
Yeah, if I may, just one final thing. Some additional piece of work that was done in the context of this paper was to check explicitly the mismodeling that can be coming from top PT. But for that, we didn't rely on the data to Monte Carlo mismodeling, because we didn't want to be biased with data. Like, I mean, we focused on the things that we have from the next to leading order calculations. And I think there is a section in the paper that describes it a little bit, what has been done in that direction to see what is the effect from the top PT mismodeling in particular.
Okay, thanks. I'll have a look.
It's Fabio speaking. Lisa, regarding your comment, I mean, what was exactly your question about you were questioning the theory solidity, or I don't know, model independence, or I'm not sure I understood your comment on the possibility of interpreting this measurement with the limit on menu color. What was your comment exactly?
No. Comment was fully experimental, Fabio, because
okay.
if before the fit, you see a slope. After the fit, in which you extract this value, you see no slope. The question is why the slope disappeared. What exactly corrected for the slope? That's all I want to know. Because of course, in the fit, you cover coupling as the free parameter, but you have like 100 other parameters perhaps. And the question is how the measured cover coupling is correlated with the pools and constraints on the other parameters.
So is this the reason why Atlas is not convinced about going after this measurement also, or what's?
No. It's just genuine interest. We have the same feeling. Something should be. Before making something ourselves, it's good to learn from the other experiment, right? Who did this measurement already?
Okay.
It's actually the opposite, Fabio. It's just because we're interested in this measurement that we want to learn from our colleagues. And we just had recently also a dedicated joint seminar about this. So you see, we want
because from the theory side, sometimes there are comments about the fact that, you're focusing really on one coupling, right? You have other electronic corrections, right, in this observable, and there are other possible effects that come into this observable from other couplings, for example, not only from the Higgs in principle, right? If you consider the next to leading order electroweak corrections to this process, this diagram is one of them, right? And so you could get a deviation from. So sometimes I heard not criticism, but warning, right? Flags raised about the fact that there could be other effects going on. So that's the reason why I was confused by Lisa's comment, because I thought she was talking about this other aspect, not the experimental or other parameters. Yeah, now I understand.
One other aspect I'm worried, I'm curious about is the effect of off-shell effects in TT bar production at high MLB, which apparently were not taken into account, or at least it wasn't explicitly mentioned. But if the full sensitivity comes from the core, from low, perhaps the effect is small. But I would still
it should be a threshold effect.
Okay.
Physically is a threshold effect. I don't know if there is some. Anyway, I wanted to say that these kind of studies, of course, to set limits are always unless you're afraid that there might be cancellation in a full calculation, but barring cancellations, to put limits or to put bounds, I think they are useful. It's pretty solid. It's a very interesting measurement.
All right, thanks everybody. I think this is an excellent example of inter-experiment and experimental theoretical discussion. If you can, we can continue this discussion with a dedicated session, but I propose to take a less than 15-minute break. Let's meet again at 5 minutes after 7 p.m. to continue with actually top properties results from Atlas, and then let's dive to EFT talks. Thank you a lot, and if you can, then please do stay connected for the topical discussion. I think this is very nice to continue.
The same link?
We'll stay in the same Zoom. Yeah.
Okay, thanks.
All right, so 5 minutes after 7 p.m., let's reconvene. Thanks, everyone. All right. We are at the time of starting the next session. Hopefully you can hear me. I'm connected from a different device. Hello?
Hi, yes, we can hear you.
Okay, perfect. I'm just checking one thing here. And yeah, let's go to the program. And we should have Kentaro. I think that was you showing us measurement of top quark properties now at Atlas. Thanks for sharing our slides. We can see them, and go ahead.
Okay, thanks. So I'm going to review the several measurements of the top quark properties with the Atlas. Okay. So in page 2, so before going to the detail of the talk, I'm quickly remind the interest of the top quark physics. And as you know, the top quark is known to be a most massive elementary particle so far we discovered, and its mass is about 173. So it is quite heavy particle. Thus, it plays quite important role both in the standard model and beyond the standard model physics. And so the study in the top quark is interesting in terms of the precision test of the perturbation QCD or electroweak interaction. And also the many beyond the standard model searches can be made from the top quark properties and something like the measurements and analysis. On the other hand, it is quite important process to understand the main background for a lot of LHC searches. So I'm still thinking so. And finally, I want to say that thanks to the high integrated luminosity and the relatively high production cross-section, we already produced more than 100 million TT-bar pairs in the LHC Run-2 experiment. So I think we can say the LHC is a top factory experiment. So this is the outline of my talk. So I will focus on the newer top property result listed here. And due to the limitation of the time, I cannot touch all recent results, but you can find all public results from the bottom link here. Okay, so first I want to start from the TT-bar spin correlation measurement in the dilepton E-mu channel. So in the standard model, top quark pairs should be produced without polarization. However, the spin of the T and T-bar quarks can be correlated. So, and let's consider the lifetime of the top quark. It is much shorter than the time scale of the hadronization, or which is shorter than the spin decoration time. Thus, the T and T-bar quark spin information is directly transferred to the decay product, and the child lepton is the one of the ideal probe to measure the spin of the top quark, because they can carry the almost full spin information. And to achieve the best sensitivity in this analysis, we are using the simple E-mu final state to minimize the uncertainties. And here the simple angle between the leptons is sensitive to the spin correlation. And in this measurement, the results are unfolded to both particle and particle level phase space. Okay, so the analysis, quick overview. So in this analysis, we are using two different event selections. And one is the inclusive selections, which is focusing on the inclusive measurement. And here we require exactly one electron and muon pairs of the oppositely charged. And at least two jets are required, and one of the jets must be B-tagged, is also required. And also we are using the reconstructed selections for the differential measurement. And here we tighten the B-jet requirement. So we require two B-jets, and also the B-tag requirement itself is also tightened. So this is to improve the top quark kinematic reconstruction. Actually, we are using the Newton weighting method to reconstruct dileptonic decaying top quark. So actually, I'm just showing the event is here. So please see the red box. So we can expect quite pure TT bar sample by using this simple event selection. Okay, so let's move to the result of the spin correlation. The two figures here showing the spin correlation result. This is actually the delta phi distribution between the two leptons. And actually, the data shown the black point and Monte Carlo prediction with spin correlation is shown by the blue histograms. So we actually observed the spin correlations slightly higher than the generator prediction. So we try to extract the FSM factor, which is the weight for the spin correlating hypothesis. And we found that FSM is actually the higher than the standard model prediction. So the FSM value is summarized in the bottom table here. And also, we also found that the FSM increases as a function of the MTT. You can see here. So, but the uncertainties also became larger. So the significance is not so huge for the differential case, but it is quite interesting behavior. So we observed some significant deviation from the standard model. So then we try to compare with the several theory predictions for this result. And here we compare the various standard model predictions. So first we compare with the higher order QCD calculation as shown in the upper plot in the other red curve. So actually this prediction can reduce the tension between the data and theory, but still do not fully agree. And then we compare with the NLO in the strong and weak couplings. And as you can see in the bottom plot in the other green line. So this agree better with the data, but we are suffering from the large scale uncertainties shown by the green bands. And also the NLO expansion with the this scale, QCD scale leads to the comparable results you can see in the blue histograms here. And again, we are suffering from the significant scale uncertainty, but yeah, interestingly, we are compare with the same expansion about the NLO prediction, but as you can see in the red histogram, this does not agree with the data. And then finally, we try to interpret this result in terms of the SUSY search. So a search is performed for the stop pair decaying into a standard top quark and right neutralinos. And so in this plot, we are showing the spin correlation distribution if we assume the SUSY particles. Unfortunately, the SUSY particle can alter this distribution, but the direction is opposite, which we actually observed. So we can set the limit on the squawk mass between 170 and 230 for most kinematically allowed neutralino mass, as you can see in the bottom plot. So this region is actually difficult to access from the direct stop search. So it is a complementary result. So then, sorry, I want to move to the charge asymmetry. So in the hadron collider, there can be interference between the TT bar production process. For instance, there is interference between the boron diagram and the box diagram. And this kind of interference can cause asymmetry in the T and T bar direction in the colliders. So, however, in contrast to the tevatron, which is the P and P bar collider, we are expecting the central and forward asymmetry in the LHC. So, and this measurement is actually sensitive, essential to the test of the higher order QCD effect. And also, if there is beyond the standard model physics exist, which can lead to the enhancement of the charge asymmetry. However, really unfortunate, this asymmetry expected to be small in the LHC because the dominant production of the TT bar is gluon-gluon fusion process. So this makes the analysis challenging. So this is a simple definition of the charge asymmetry measurement. So we are just observing the delta-y distribution, this defined here. So this is the analysis overview. This analysis is made with the single lepton final state, focusing the both resolved and boosted topologies. And we are measuring the charge asymmetry inclusively and differentially as a function of the mass of the TT bar system and the beta Z of the TT bar. And the Bayesian unfolding procedure is applied, and the systematic uncertainties are profiled as a nuisance parameters, like here. So this is to minimize the uncertainties. And in this figure, I showed the high-ranked systematic uncertainties. So the most dominant uncertainties are the ISR modeling. So this is the TT bar charge asymmetry result. And the three figures shows the inclusive result and differential the function of beta Z and MTT respectively. So let's see the first, the inclusive measurement. We are observing the 0.6% plus minus 0.15%. So this is actually 4 sigma deviation from the zero assumption. So, but we try to compare with the higher order QCD and NLO Electroweak calculation, and also compare with the Monte Carlo generator. So we can see that some tension between the MC generator, but the measurement is really consistent with the higher order calculation. So actually, this is the first evidence for the charge asymmetry in the PP collision. And we also try to measure the differential. And actually, the results are consistent with the theory calculation. Then we try to interpret this result using the EFT approaches. So for this case, the inclusive and MTT measurements are interpreted in the EFT framework. And we try to derive the limit on the linear combination of the some of the Wilson coefficient for the dimension 6 operators. And the result is summarized in this figure. So both inclusive and some of the differential case, we can set quite tight limit on the this linear combination of the Wilson coefficient. So especially in this MTT bar beam between the 1000 to 1500, we can set tightest limit on this factor. So actually, we compare with this previous LHC results and Tevatron results. The limit we achieved is tighter than the previous measurement. So then let's move to the top-quark decay width measurement. So the top-quark decay width is one of the fundamental properties. And due to large top-quark mass, the decay width is also expected very large. For instance, this is the most precise theoretical prediction in NL precision. The decay width is expected to 1.3 giga-electron volt at the mass here. So, however, we can expect some possible deviation from the standard model if there is such process, top-quark decaying into a charged Higgs boson, or there is some decay flavor changing neutral current process, or if there is some modification of the CK matrix element like a BTV. And this analysis is direct approaches to measure the decay width. So unfortunately, this approach is less precise than the indirect approaches, but they're less model dependent. So the both direct and indirect approaches are complementary analysis. So this is the analysis overview. So this analysis focuses on the TT bar events in the dilepton decay channel, and 2 leptons and 2 jets are required. And only for the same flavor channel, because they have a significant background, that the DMAS better is applied, and the all channel we apply the drill one better. And also for the same flavor channel, we are requiring the tight missing ET cut to eliminate D plus jet background. So as you can see in the event table, we are actually requiring quite tight a cut. So the number of events in the same flavor channel is not so significant, but yeah, we can expect such improvement by using 2 channels. And then we try to use the profile likelihood fitting, template fitting technique. So the template is prepared using different top-quark decay widths. And the simultaneous fitting is applied for all 3 different channels.
Kentaro, you have about 4 minutes, I think.
Okay, I must be quick. So, okay, so this is the result for the decay width. So the measured decay width is 1.9 plus minus 0.5 gigaelectron volt for this top-quark mass. And I just listed the significant uncertainties in this table. So the dominant uncertainties are the jet reconstruction and signal and background modeling and DMC statistics. So, but the measurement is in good agreement with the standard model predictions. And this showed the pre and post-fit distribution for the reconstructed MLB. So this MLB is actually sensitive to the, so this is the partial top-quark mass, but still sensitive to the decay width. So we are using this distribution to extract the decay width. So finally, this is actually touched in the previous session, but I quickly review this result. So this is the lepton universality in the double boson decay. So we are measuring the branching fraction ratio defined here. So this ratio has been measured by LEP experiments, and there is some gap from the standard model expectation. So this motivating the precise measurement at LHC. So this analysis measures the branching fraction using the dilepton TT event. So this gives an excellent double boson sample. And so here we are assuming the branching fraction to tau to mu1, which is well known. So we can simply measure the event number of the double to tau nu, then decaying to mu1. So the analysis quick detail. So in this measurement, we are using the tag and probe approaches to tag the probe muon. This is directly decaying muon, and also using the muon from the tau decay. So which had the softer PT distributions, and they have the different displacement of the decay vertex D0, as you can see in the bottom figure. So for the background, the significant background is the Z plus Z and the fake muon. So we try to calibrate this normalization using the different signal control regions. So this is the result. And so to estimate this ratio, we are using the profile likelihood fitting, which is performed to the two-dimensional PT and D0 distributions for each EMU and MIMI channels. And observed ratio is quite close to the unity, and the result is summarized in this figure. And yeah, actually this is consistent with the standard model prediction, and also compared with the previous rate measurement, we can set we achieve the more precise measurement. Okay, so let's go to the summary. Atlas performed the various top property measurement, and we are showing the spin correlation result here. And we are observing some significant tension between the data and theoretical prediction from this measurement. And this suggests our limited understanding of the top-quark production and decay. And this top charge asymmetry measurement, we are now also able to see subtle higher order effects in the top quark properties, such as the charge asymmetry tiny effect. And in the top quark decay width and the tau nu branching fraction ratio measurement, the standard model is still powerful to describe the data. And a lot of the other results are in pipeline, so stay tuned in the top property measurement. And that's it from my side. Thank you very much.
Yeah, hi, perfect. Thanks for getting back on time. And so questions from participants? Should be able to see raised hands, hopefully. Got many people again. I don't see a hand raised, but go ahead in case there is. I just don't see.
Maybe a quick question about spin correlation. This is Gauthier Durieux speaking. So I think CMS is discussing extensively with theorists about this discrepancy between the measurement and the prediction. What is the status on the Atlas side? Are you performing also, and maybe I should say they've identified a few points of modeling, for instance, of the top, which could explain that discrepancy. So in Atlas, are you also looking into that and comparing more closely with theory predictions?
Actually, I do not so familiar with the recent progress about this measurement. So maybe I hope there is someone can comment on this in this room.
Okay, no problem. Thank you.
Sorry.
All right. Other questions?
So this is Francesco speaking. Maybe I add a bit more to this. So as you see, Atlas has actually played a significant role in making progress on this, because from the preliminary results that we had out to the paper that we have now finally got accepted after all the developments, a whole series of calculations were included just to try and understand the differences between the data and the prediction. And you notice that, first of all, the tension that one notices is with one specific NLO plus PS prediction, which is pi plus Pythia. But NNLO, depending on the calculations, expanded calculations, both NLO expanded and NNLO expanded, these calculations that you see on top of these results in slide 7, these are the result of interaction with theorists. And these were interactions that came out of the discussions that Atlas also has brought forward over the past months between the preliminary Atlas results and the paper. And these results are included exactly in the paper. And if you want, that's the result of this whole effort in trying to probe the theoretical community to make progress on this. And you notice that the expanded or not expanded calculation from the point of view of the prediction in the bottom right plot do not make this gigantic difference. What is interesting is that the NNLO still comes closer to the data, but still behaves a bit more discrepant with respect to the data. Discrepant is a strong word. I mean, it has a bit more tension with respect to the data. While this additional theoretical way of calculating the prediction, these NLO expanded prediction or NNLO expanded also allow an additional comparison of all the different effects. So the reason why the NLO QCD weak or the NLO expanded, which don't make a lot of difference between all of them, go closer to the data, and on the other hand, NLO, whether expanded or not, still shows more a tendency to deviate, especially in the extreme region. This is yet not fully understood, but if you think about the initial picture where one had one NLO plus PS prediction and one NLO expanded, and the picture that we have now, we have definitely increased our knowledge, right? We have the NLO, we have the NLO expanded, and the discussion will keep on going. Let me make one final statement that if you want, the ball is at the moment a bit more on the theory side than on the experimental side. Because if you've seen the previous presentation by Giulia in the previous session, Atlas and CMS are just on top of each other, experimentally speaking. There is complete agreement between the experimental measurements.
What I had in mind, I don't know if there is time to expand on that discussion. Maybe the chair should tell me.
Not much, actually.
Okay.
Yeah, but can you connect to the discussion after the session so that we don't cut it?
Sure.
All right, perfect. Thanks. Thanks, Kentaro, really, for this talk at this crazy hour back in this country. Yeah, I think we really have to move on to the next talk, and I think we should have Samuel to be presenting results on FCNC and EFT by CMS.
Okay, thanks.
Yeah,
Hi, can you hear me okay?
Can hear, we can see you. Hoping you can share your slides as well.
Great, I'll start sharing. Okay, so today I'll present some results from CMS on flavor changing neutral currents and effective field theory interpretations in top quark events. So first I want to start with standard motivations for new physics. There's of course strong evidence for dark matter and dark energy. And additionally, there's some aspects of the standard model which are theoretically unsatisfying. So there's the hierarchy problem. In other words, why is there such a large order of magnitude difference between the scale of electroweak symmetry breaking and the Planck scale? There's the observed matter-antimatter asymmetry in the universe. CP violation can account for some of this, but there is not nearly enough CP violation observed in the weak interaction to account for this huge discrepancy that we see. And then there's the strong CP problem, essentially the fact that while the QCT Lagrangian permits CP violating terms, we have no observed evidence of CP violation in the strong interaction. So given these strong motivations, why haven't we found new physics at the LHC? One possibility is that the scale of new physics is beyond the energies which we can directly access at the LHC. So supposing this is the case, would we still be sensitive to signatures of new physics that live beyond the energy scale directly accessible at the LHC? And if so, how would we probe this? One way is through the top quark. So many BSM theories result in measurable deviations of either the top quark's interactions with other particles, or they allow for interactions which are forbidden in the standard model at rates which are accessible to us at the LHC. So there's a diverse set of theories of physics beyond the standard model, from supersymmetry models to 2 Higgs doublet models, warped extra dimensions. And this wide array of BSM theories can all lead to similar signatures at the LHC, which can present themselves in the form of modified top interactions or flavor changing neutral currents. And so these are the 2 focuses of my talk today. So first, a word on an effective field theory interpretation framework. Given the fact that we have this wide array of theories beyond the standard model, we would like some way to interpret the results of these measurements in a way that is agnostic to any particular BSM theory. And so the effective field theory framework, loosely speaking, can be thought of as a sort of Taylor expansion of the standard model. So we express a Lagrangian as the standard model Lagrangian plus dimension 5 and dimension 6 operators. In general, the dimension 5 operators correspond to things like neutrino masses or generate lepton number violation. So these are less interesting in the context of top quark events. And we're particularly interested in the dimension 6 operators, which can correspond to flavor changing neutral currents, chromomagnetic or chromoelectric dipole moments, etc. So first I'll go through some results from CMS on modified top interactions and their interpretations in an effective field theory framework. So this includes a variety of production modes and final states, including TTZ, 4 top searches, and a variety of TT bar plus X final states. So starting with effective field theory and top Z interactions, this analysis from CMS measures inclusive and differential cross-section measurements of TTZ production in 3 and 4 lepton final states. And the core EFT strategy in this analysis is to simulate the signal samples in a fine grid of the Wilson coefficient parameter space. In other words, the coefficients which affect the dimension 6 operators in the effective field theory framework. Then a 2D reweighting of the sample is derived, and this allows the analysis to produce predictions which are parametrized as a function of the Wilson coefficient values. And the analysis then extracts constraints on electroweak dipole moments, for example, as well as anomalous neutral currents interactions. Next are searches for standard model for top production. And these are also covered in more detail in another talk from Andrea Castro, which I've linked here. The broad strategy of the analysis is a selection that is based on BDTs trained on event level kinematics. And then the EFT component is cast in a reinterpretation of the cross-section upper limit in the context of 4 EFT operators which contribute to 4 top production. And so the constraints are shown in the bottom left and are in agreement with the standard model expectation. Next is an analysis which searches for TT bar and TW processes in the dilepton final state. And this analysis exploits a neural network dedicated to separating between TT bar and TW events. Although they have very similar final states, exploiting the having separation between the two allows us to exploit the sensitivity of the TW process to new physics. And so similarly, these processes are simulated to detector level under the presence of new effective interactions. In other words, parameterized as a function of the Wilson coefficients. And this allows us to determine fitted values, correlations, and uncertainties directly from fits to data. Again, a variety of Wilson coefficients have constraints placed on them. And again, the results are in agreement with the standard model. Another topic which has been covered in a few previous talks today is using the studies of top quark polarization and TT bar spin correlations and interpreting these results in an EFT context. So generally the analysis expands the polarization vectors in the spin correlation matrix into an orthonormal basis and probes these through differential cross-section measurements. The EFT interpretation comes in by deriving constraints on, again, the dimension 6 operators. And the Wilson coefficients are then expressed in terms of these polarization and spin correlation coefficients. So this allows the analysis to cast predicted yields as a function of the Wilson coefficients, and again, determine best fit values and uncertainties directly from fits to data. Finally, the last analysis in the context of the EFT interpretations is a very new result from CMS, which has a novel approach to EFT. In general, the standard EFT approach that has been followed is to search for a specific process or a specific final state that is sensitive to a few Wilson coefficients. But this analysis takes a paradigm shift, and rather than searching for specific processes, it searches for a wide range of processes in the multiple lepton final states. And the predicted event yields are parametrized as a function of all of the relevant Wilson coefficients, and this is done for all of the relevant processes. So to go into a little more detail on the parameterization, the yields for processes containing prompt leptons are taken from simulation and then parametrized as a function of the Wilson coefficients, while processes with non-prompt leptons are predicted from extrapolations from control regions. And in general, this allows us to express an arbitrary matrix element as a sum of standard model and BSM contributions. And this can be then translated to a cross-section, which can then be translated to predicted event yields as a function of the 16 relevant Wilson coefficients that contribute to top-quark production. And these 16 coefficients and their fitted values are shown on the right here. There are two scenarios for fitting a given Wilson coefficient. The first is that all of the others are allowed to float freely. And the second is that all of the other Wilson coefficients are set to their standard model values of 0. And so due to the fact that there are degenerate minima in some of these scans, a 2 sigma interval is not clearly defined in some cases. And so in these cases, scans of pairs of the coefficients are performed. And I think one of the main takeaways of this analysis is the novel approach to the EFT interpretations that it pioneered. And so it uses the multi-lepton final states, which serve as a good illustration of its power, but really this is broadly applicable to many other physics processes and a wide range of final states. And finally, one last word on the EFT interpretations. Here's a nice plot produced from the top group at CMS, summarizing the constraints on Wilson coefficients for interactions between top and scalar bosons. And there's a corresponding plot in the backup for top fermion operators. So next I'll go through results from CMS on searches for flavor changing neutral currents. And I want to motivate this with a hypothetical discovery story, which has not yet been ruled out at the LHC. So flavor changing neutral currents are of course forbidden at tree level and can occur through loop diagrams, but these are heavily suppressed to a rate well below what we're sensitive to at the LHC. And 2 flavor changing neutral current models, first with the Z as a flavor changing neutral current and next with the Higgs, are well motivated by a range of BSM theories. And some of these predict branching ratios, which could be on the order of 10 to the -5, 10 to the -4, which has not yet been ruled out by the LHC. And beyond this, some of these models could predict branching ratios for T to ZC and T to HC on this order, but all other flavor changing neutral current processes well below LHC sensitivity. So this especially motivates the need for studying these channels. In general, we can have 4 different types of flavor-changing neutral currents, either through the gluon, the Z, the photon, or the Higgs. Results on the gluon and photon from CMS are covered in the backup, and I'll focus now on the Z and the Higgs. First, with the Z as a flavor-changing neutral current, this analysis looks at final states with 3 leptons and between 1 and 3 jets. And the general analysis strategy is the use of separate BDTs targeting both single top as well as TT bar production modes. The observed exclusion limits are on the order of a little bit above 10 to the -4. Again, not ruling out this hypothetical discovery story I mentioned previously. Next is a search for the Higgs as a flavor-changing neutral current, looking in the BB bar decay mode of the Higgs. The analysis strategy is similar. It uses a BDT-based approach and searches for both single top and TT bar production modes. And the observed limits are similar in order of magnitude, what we saw for the Z. They're slightly above the order of 10 to the -4. So this hypothetical discovery story that I mentioned is still not yet ruled out by the current limits we have from the LHC. And so this really presses the importance of continuing to study flavor-changing neutral currents with the full run-2 data set. Finally, to wrap up, we have these very well-founded motivations for the presence of physics beyond the standard model, but we've not yet found new physics at the LHC. So perhaps the scale of new physics is beyond the LHC's energy reach. And this motivates searching for more subtle signatures of new physics. And this is done in 2 ways in CMS, at least 2 ways that I covered in this presentation. The first is looking for modified top interactions. In other words, small deviations from standard model predictions. And the second is through flavor-changing neutral currents, which are not allowed in the standard model at tree level. And so any observable evidence of flavor-changing neutral currents would be a clear indication of new physics. Finally, the effective field theory approach allows us to cast these results in a way that is independent of any particular BSM theory. And so far, the results from CMS are in agreement with the standard model. But despite not yet seeing any signs of new physics, we're still confident that there must be physics beyond the standard model. And so this really motivates the need for continued searches for new physics using both the effective field theory approach as well as searching for flavor-changing neutral currents, both with the full run-2 data set and beyond. Thank you.
Okay, thanks very much. Thanks for staying on time. Thanks for this nice introduction to the topic as well. And questions?
Hello. Do you hear me? Francesco
Yes.
speaking.
Go ahead, Francesco.
Yes.
Thank you, Samuel. This was really very interesting. So, of course, I'm interested in the new kid on the block. So slide 12, 11 and 12. Will you tell us a bit more about how this parameterization is set up? I mean, from a technical point of view. I see that there's a variety of samples that are involved. So you say that you're parameterizing the samples that they're contributing prompt leptons, i.e., all the modifications to TT plus X, W, Z, whatever that is, as a function of the EFT operators. But how is this done in practice? Does Does it mean that one is generating many samples with different values of EFT parameters? Or does it mean that one generates one sample and then one uses a reweighting scheme to obtain the other sample? And is this a profile likelihood fit, or is it just a fit and then uncertainties are propagated in a standard way? Will you elaborate a bit more on these details?
Sure. My understanding is that there are many samples generated rather than a reweighting, but I believe some of the authors are connected. Hopefully they can confirm or deny this. And to your second point, the fits are performed in two ways. First, with all of the other coefficients left floating, and second, with all of the other coefficients set to 0, the standard model value.
So I see what you connected, but also maybe. Is there another answer to this question?
No, it's a question on my side.
Can you hear me?
So there's Gautier connected, raised hand first, yes.
But that was a question. So maybe you want to answer this one first?
I think one of the authors wants to answer the question, Andrew.
Yeah, so as far to the question about how the samples are produced, we actually do make use of reweighting. So we basically produce a single sample for each of the process, and then we use we attach a bunch of like 183 reweight points, and then from there we extract a parameterization for the 16 Wilson coefficients for each sample.
Thanks for correcting me, Andrew.
Okay.
But how the fit was done, this question wasn't answered, sorry.
So it is a likelihood fit. Maybe Andrew can comment again on the details of that.
Yeah, so it's a profiled likelihood fit, and we basically we essentially parameterize our histograms in terms of the Wilson coefficient on a bin by bin basis, and then we basically hook those up to combine, and which is the thing that performs the fit, or the software that performs the fit, and then basically turns the knobs on the Wilson coefficients to find the set of values that best matches the data.
So to complete, I mean, there is no propagation of uncertainties. They are determined in the profile likelihood.
Yes.
Can I ask something related to this?
Oh, if it's related to this, because Gautier has been having his hand up for a while, so.
Yeah, it's also related to this.
Okay, so then Gautier first. Sorry, no.
It's very nice to see those results indeed, especially the full famine one, which I think I've never been constrained so far. I mean, it's a very short question. I see in those few cases, the individual constraints in red are actually looser than the profiled ones, and I don't quite understand how that can be the case. Can you comment on this?
So the question was why the frozen ones or the fixed fits are wider than the profile or the simultaneous ones?
Yes, in some cases.
Yeah, right. So that's because when you fit to the data, there's because the Wilson coefficient, or because the parameterization is this n-dimensional quadratic, you get a double. You can end up with a double minimum. And if that double minimum appears far away from or far away from the standard model, it will it widens the 2 sigma confidence intervals. But when you do the full simultaneous fit, the double minimum basically kind of disappears, and then you just have like a single flat minimum, which is why for some of these it can appear as if the simultaneous fit is narrower than the single parameter fit.
But the input data is the same in the two cases. So how can the marginalized one, the profiled one, be more constrained?
Because I mean, in the frozen one, you're fixing all of your other Wilson coefficients to the standard model. So you're fixing it to a specific value. Whereas when you're doing the marginalized value, you're allowing them to like kind of float around and compensate for one another.
Yeah, this I understand, but I would expect then the bound to be looser. But okay, can we discuss that later?
Yeah, sure.
All right, I see Nuno's hand.
Okay, it's related, sorry, but I still didn't got the procedure. Probably I need to read the notes. But this fit at RICO level, and you take into account the generated samples and at RICO level, considering acceptance corrections and everything, or it's basically a dependency on the cross section that you measure, that you interpret in terms of these Wilson coefficients?
I believe it takes into account the detector effects as well. Is that true, Andrew?
Yes, it's at RICO level.
So basically you take all the measurements with a breakdown of uncertainties and do the combined fit. Is it right?
What do you mean, Lisa, by all the measurements? Because there are no separate measurements. There is one single measurement doing all this at once.
Okay. Okay.
It's not a combination of measurements, right? It's that, if you go to the previous page, previous slide, it's that distribution that we're looking at, right? It's those yields that are all fit together, as far as I understand. Is that correct?
Right.
Mm-hmm.
Right. I think we should move on to the last presentation of this section, and then we can continue the EFT discussion in the dedicated discussion one. So yeah, I think we should have Cornelius presenting the enhancing of SMEFT Wilson coefficient fits.
Yes.
Yes. Thank you.
Okay. So I hope you can see the slides.
Yeah, I can hear you. Perfect.
Very good. Okay. So yeah, I'm Cornelius, and I would like to talk about enhancing fits of SMEFT Wilson coefficients in the top quark sector. And so what I would like to start with is a short introduction to the SMEFT, the standard model effective field theory, which we already heard about in the previous talk. So the SMEFT is basically an effective extension of the standard model Lagrangian using higher dimensional operators. So we know the standard model has a mass dimension of 4, and then we can construct higher dimensional operators using some standard model symmetries and using the standard model fields, and then we construct the new operators. And if you do this in dimension 5, that's basically just one new operator, which would contribute to neutrino masses. But if you then go to dimension 6, these would be the leading contributions to BSM physics. And as you can see, they are they need to be divided by the energy scale, lambda, but to the square. And all of these higher dimensional operators, they have this Wilson coefficients, which are some kind of coupling strength of this operator. So if the Wilson coefficients are 0, we obtain back the standard model. And if we find, by constraining the values of the Wilson coefficients, if we find deviations from 0, this would be hints to BSM phenomena. And so what I would like to talk about in this talk is that there are a lot of BSM models, as we've heard before, that predict especially deviations in the top quark couplings. And there, in the top quark sector, there are several efforts ongoing that want to constrain the Wilson coefficients of those dimension 6 operators. Right. And so I would like to present 2 studies that we performed. in order to investigate some aspects that might help to enhance SMEFT fits. And the first thing I would like to talk about is including observables from B physics. So the idea here is that some of the operators that contribute to the top quark sector also appear in B physics observables. And so they might be constrained by a combined fit. And the example we considered in our studies is the top photon coupling. And in the top sector, there are measurements like the TT bar gamma production cross-section. And so there's, of course, the top photon coupling, but in some B processes, especially in something like B to S gamma transitions, since they happen via a top loop, there might also be a top photon coupling, and this could also be changed by the same operators, basically. And so for our studies, we take a look at the TT bar gamma production cross-section and the branching ratio of B bar to XS gamma, and we want to combine measurements for them in one fit to constrain Wilson coefficients. And let's first start with the TT bar production cross-section. So in the top, you can see some diagrams that contribute to this cross-section. And so we consider here three different operators. We have OUG, which basically modifies the coupling of the top to the gluons in these in the left two diagrams. And then we also consider the operators OUB and OUW, where the U is always referred to, or is always the top quark in these cases. And those two operators affect the top photon coupling. So, and we want to constrain these three, or the Wilson coefficients of these three operators. And we want to do this by using a fiducial cross-section measurement performed by Atlas at 13 TeV. And to do so, we need to somehow know how this cross-section depends on the Wilson coefficients. And to do so, we perform several computations with MATGRAPH and the DIM6 top UFO model, which allows to calculate cross-sections for any given configuration of Wilson coefficients, so to say. And this is very nice. The only problem is these Monte Carlo simulations take a bit too long to be directly interfaced into the fit. So we first need to interpolate and get a fast parameterization. And as we already heard, we can do this by using a quadratic polynomial, since the dependency of the cross-section on the Wilson coefficients is basically quadratical. So the linear term is something like the Wilson coefficient times the interference between standard model and BSM contributions, which is the leading BSM term. And then there's also something 1 over lambda to the 4, which is something like is quadratic in the Wilson coefficients. And then if we sample at various points within the parameter space of the three Wilson coefficients, we can then just interpolate these quadratic functions through all of these points. And we can do this, and what we get out is basically, if we use MATGRAPH DIM6 top and this interpolation, we get something like the total cross-section if we do this on parton level. The thing is that the Atlas measurement is a fiducial cross-section measurement, and that's why we also perform an event selection at all the sampling points that we look at. And so we want to calculate the fiducial acceptance with this, and we can also do this and then interpolate this, because the fiducial acceptance is something like a ratio of two quadratics. And so if we then take the product of both, we basically get the fiducial cross-section as a function of the three Wilson coefficients. And what you can see here is the result for the single lepton channel. We also did this for the dilepton channel. And so you can see here the quadratics when only one of the Wilson coefficients is varied and the others are set to 0. And you can also see the measurement with which we want to compare. And yeah, the dilepton channel has a pretty similar shape of those three Wilson coefficients. So this was the top part, and we also want to constrain using this B measurement. And the thing is that in B physics, there's usually a different formalism used. So in top physics, we have the SMEFT Lagrangian, which I showed you, and the three operators I showed. But in B physics, there's this weak effective theory, the WET, is often used, and
these describe the same physics, so to say, but with a different set of operators. Especially for us interesting are Q7 and Q8. And so we first need to translate these. And if you take a look at the energy scale, so on the left is the energy, up here is the energy scale lambda, which is the energy of the full theory of standard model and BSM particles. And we would like to know where this is, but we're currently here at the standard model energy, so somewhere at the top scale, and the wet theory lives down here without, so it's an effective theory also, so it has no top Higgs or heavy bosons. They are integrated out within this theory. But of course, we can go from the one set to the other set, and this we can do by running and matching. So to get from SMEFT to the wet, we need to first run in the SMEFT with some renormalization group equations. And then at the matching scale, we can match the SMEFT operators to the wet operators, and then we can run down into, to the energy scale of the wet. And this is what we do. And why do we do this? So we do this because the calculation of the BSM contributions to the branching ratio of B bar to XS gamma is known in terms of these wet operators. And if we do this matching, it looks somewhat like this. So delta C7 is something like the BSM contributions to this C7 Wilson coefficient of the wet. And this depends on CUW and CUB from our SMEFT coefficients, and C8 depends on CUW and CUG. So we can then put this matching in, and then we can calculate the dependency of the branching ratio as a function of the three SMEFT Wilson coefficients. And this is what can be seen in the plot here. So you again see a plot where only one of the Wilson coefficients is varied at a time. And you also see the measurement. So for us, if we use the measurement, that is basically a combination of multiple measurements done by the heavy flavor averaging group. And this is shown here. And you can see that the largest influence on this branching ratio comes from the operator CUB. Okay, so now we have basically everything together we need. We have the Monte Carlo simulations and interpolations to give the dependency for the top processes, and we have the fiducial measurements from Atlas for the TT bar gamma. And for the B physics part, for the branching ratio, we have the theory calculations, which we get by doing the matching and running. And we have this combination value from the heavy flavor averaging group as our data. And then we could put all of this together in one fit. And for the fit, we use a Bayesian approach using the Bayesian analysis toolkit in Giulia and the EFT fitter. And the results we get look somewhat like this here. So what you can see here are two-dimensional marginalized posteriors from a fit where all three Wilson coefficients are allowed to vary. And what you can see are the smallest areas that contain 90% of the posterior probability. And in both these plots, the areas that are gray correspond to a fit where we only use the information from the B physics, so only the branching ratio as a measurement to constrain all three operators. And in light blue, you see the same for only the top measurements, so only the TT bar gamma cross sections for the light blue. And in the dark blue, there's the combination for a fit where we use both. And as you can see here, in both of these plots, which is on the left is CUB versus CUG, right we have CUB versus CUW. And in both these plots, the constraints we get from only the B measurements correspond to something like 12% of the whole parameter space. So from -1, this square from -1 to 1 in both operators. So this would be 12%. For the top measurements, it's of the same order. It's something like 11%. So it should be a filled donut, so to say. And so the combination is just about 1% of this allowed region. And so what you can see here, at least in this proof of concept study that we performed, that the combination of top quark and B observables improves the constraints, and for this case by up to a factor of 10. And so this might be a very interesting region to look into and to consider for future fits. So this was the first thing I wanted to talk about. And the second one is that I wanted to show what the impact of correlations between the uncertainties of measurements that are included in SMEFT fits are. And so global SMEFT fits usually include many measurements and different observables, and the uncertainties of the measurements that are included are often correlated. But the problem is that determining the correlations between the uncertainties is not so straightforward, especially if you want to combine measurements from different experiments or different runs of one experiment or so. And that's why often in SMEFT fits, correlations are neglected. And so we asked us, do correlations even matter in SMEFT fits? And that's why we wanted, or that's why we performed a study to investigate the influence of correlations on the results of a SMEFT fit. And for this study, we took a look at the different processes, and we looked at T-channel single top production and also some top decay observables like W helicities and top width. And we considered 4 of the dimension 6 operators. OTW is basically the same as OUW before. And then we have O5Q3, and those two modify the coupling of the top to the W boson in this diagram here. And then we also consider OQQ1 and OQQ3, which are for fermion operators. And so the only thing is that in the processes we consider, there's only a linear combination of those two that contributes. So we have, for fit, we have only 3 independent parameters, which are C5Q3, CTW, and CQQ. So, and we want to constrain these 3 coefficients by using several measurements. We use 55 different measurements of 41 different observables. And as I said, we have T-channel cross-sections. We consider total and differential measurements from ATLAS and from CMS at all 3 energies. And for the decay, we have W helicities and top width measurements from ATLAS, CMS, CDF, and D0. And so if I say measurement, the distributions, so the bins of the distribution, we count as one measurement, so to say. And all of these measurements typically have uncertainties, and we categorize them into 3 categories, which are statistical, systematic, and theory uncertainties. And so the setup of the fit is similar to the one I showed you before. The model for the dependency of the observables on the Wilson coefficients, we again determined by using Monte Carlo simulation and this interpolation. And this time we not only used the quadratic parametrization for the cross-section, but also the linear, and to just see how they compare. And the measurements are what I showed you on the slide before. And then the question is, what happens if we include the correlations of these 3 categories of uncertainties? And then we put this all again into a fit with the EFT fitter. So the correlations would be, in this case, since we have 55 measurements, there would be 55 times 55 correlation matrices for each of the 3 uncertainties. For the statistical correlations, they are often given, especially for the bins of the distributions. So so we can use these numbers, and other statistical correlations we assume here to vanish, since typically these are independent events. For systematic and theory uncertainties, it's a bit more complicated, since there's no information provided typically. So we need to have some simplifying assumptions and some parameterizations, and this is what we call here our best guess scenario. And let me just show you our best guess scenario for the systematic correlations. So there we have, so this is not the full 55 times 55 correlation matrix, but just a short representation. So this here would be the single top cross-section measured from ATLAS at 7 TeV, this ATLAS at 8 TeV, CMS at 8 TeV, and some top width. So yeah, and the assumptions that we made to construct these big correlation matrices are that the same experiment and the same energy measurements performed at this should have, or the systematic uncertainties from them will probably be rather strongly correlated. And for measurements at the same experiment and different energies, they are less strongly correlated. And the systematics of different experiments we assume as uncorrelated. And we need to do similar assumptions for theory correlations, with a little bit different assumptions, of course. And then we need to choose a value. And we just chose a rather strong correlation of 0.9 for both. And if we take this as our best guess scenario and we perform the same fit once with the best guess correlations on the right and once without on the left, this is what we get. So here we have again the results of fit where all three coefficients are free to vary. And we see the marginalized best fit values in the smallest 95% intervals. And as you can see on the left, we have a pretty good agreement with the standard model in all of the coefficients. And the linear and quadratic are also a very good agreement. And for the right, with the best guess correlations, we also see that linear and quadratic are in good agreement, but we have some rather strong deviations from the standard model in one of the coefficients. And we, of course, we performed some more studies on this and used different values for the correlation coefficients, but we saw a consistent behavior that for larger correlations, the deviations get stronger. And so the last point I would like to quickly mention is that we also took a look into the future, so to say. So we tried to scale the statistical uncertainties, and we scaled them to 300 inverse femtobarn, which would correspond to the luminosity or integrated luminosity of LHC round 3. And in the left plot, you see now the best guess correlation scenario with statistical uncertainties scaled to 300 inverse femtobarn. And you can see when you compare with the plot I showed before with the current data, you can see that the deviations in C5Q3 get even stronger. And also in the other two coefficients, there would then be some deviations from the standard model to observable. So, and just to summarize and conclude, I showed two studies, and the first one was that we performed the first consistent fit using top-quark and B-physics measurements to constrain the SMEFT Wilson coefficients. And I hope we could show that this might be very beneficial to include this in global fits of the SMEFT Wilson coefficients. And the second part was that we performed studies on single top and top decay measurements, studying the influence of correlations by comparing the a best guess correlation scenario to no correlation scenario. And what we could see there is that the correlations do matter in such fits, and in the future, they might even matter more. So yeah, thank you.
All right, thanks a lot for these nice strong results, especially the correlation treatments and the improvement when combining different methods. So I see Suzanne has a hand raised. Go ahead.
Yes, thank you. Can you hear me?
Yeah.
Good. Thanks a lot for your good talk. I have two questions. Let's start with the first. So it's on page 6. You talked about a fiducial cross-section for TT-bar photon production. I was wondering if the acceptance that you include is at the parton level. So if you basically keep top stable and what you call A would just include the phase space acceptance, or if this also includes acceptance due to top decays, potentially detector effects. So at what level do you compare?
Okay. Yeah. We calculate this at particle level. So the top is decayed into a jet, but there's no detector simulation.
So this means that you basically include photon radiation in the top decay, which I think is significant, right? So there's a significant interference between photon radiation from the top decay versus photon radiation from top production.
Yeah, I think so. So we did not explicitly look into this, but yeah. So
okay, but if you compare at particle level, then it should be taken into account. So that would be good.
Yeah, I think so. So it's after running Pythia on the mud graph events, basically.
Okay, and then my second question, if I may. I remember for your correlations work that you compared with our previous analysis, where we also took into account correlations, but we assumed them to be either 100% or correlated or not at all correlated, right? So now I think you assumed a 90% correlation, and I remember from your paper that you found a good agreement within, I mean, slightly different treatment of observables and the approach, right? So the question is, at what level would you be sensitive to a variation in correlations?
Okay. Yeah, so first of all, we just took 0.9 because the very strong correlations of 1 sometimes lead to some funny effects, so to say. But as I mentioned, we performed studies varying these values. And what you can see here is, for example, for C5Q3, these are the marginalized results for C5Q3, and here we vary the coefficient of the correlation coefficient. And you can see that from maybe, what is it, 0.4 or 0.5, then there you get deviations from the standard model that are more than the 95% interval, so to say. Yeah. So this would be, I don't know if this is what the sensitivity you
hints, I think it hints at what I was looking for. Are these in the paper?
These are in the paper, yeah. So basically, we will very soon upload a new version to archive, because we had to do some minor changes, and some plots changed a bit, but the agreement got better, so to say. Because yeah, so we compared to a third scenario, not only linear and quadratic, but a third in the paper, which I did not show here. And then we now get a better agreement, and this will be updated very soon.
Okay, thanks a lot. Very good.
All right, thanks. We have Lisa.
Yeah, also on this correlation study, I find it very interesting and very important. Can you call it? It was on slide 19, I think, when you showed that without taking, no, I think it was 18, sorry.
Yeah, okay.
So no correlation versus best guess. So it's exactly same measurements. So can you remind me how many measurements here?
These are 51 measurements. So
51 measurement.
55, yeah. So but we count each bin as one measurement, so to say.
Each bin, so
yeah.
You mean you include distributions?
Yeah. So we have differential cross sections, like here cross section as a dependence of photon PT, also a top PT. So.
Right. So in principle, you do see, if you look at all those measurements by eye, you do see some deviations, right, from perhaps the prediction. But in the fit, they become significant only if you take into account correlations. Is it what these plots are telling me?
I'm not quite sure what you mean.
Well, if I have 50 measurements, completely, expectation is on top of prediction. There is no any suspect in terms of disagreement with the standard model.
Yeah.
How can I, whatever correlations are, I shouldn't be able to see this pool. So it means that intrinsically in your measurements, there were some deviations from the standard model, but perhaps they were not significant enough. If you don't take into account correlations, you don't actually see it. But if you do take into account correlation, you see it. Is it?
I think that's the point, because of course the uncertainties are not big, but as you can see on the left plot, they are so big that they cover the standard model prediction. And just if you would include the correlations, this would shift away from the standard model even farther. Yeah.
Right. Okay. And I believe that's a very important point, that the more statistics we have, the more important correlations are, right? Because this uncorrelated component becomes very small. Okay, but what needs to be provided by the measurements to take this in the best way into account?
Yeah,
because clearly the conclusion depends on what you assume. You can even parameterize, right, the correlation versus the effect.
Yeah, sure. So the correlation we use is the best guess, and we use the information that's available and thought of a reasonable parameterization of the correlation metrics. But so yeah, in principle, to do it really right, one would have to do the combined likelihood of all the measurements. But this is, of course, it's very hard and maybe not even doable. So at least, so the least thing the collaborations can do is provide the correlations for the measurements they perform and between the bins, and maybe compare to different runs or the different energy scales for the measurements also. So
yeah, I'm not sure about 7TV, but perhaps now, since we put things in HEP data, that becomes, in fact, much more possible.
Yeah, I think that's a good way to get more information of correlations. Yeah.
Thanks.
All right, thanks for this nice discussion. Any other hands raised? I'll just ask freely. I think we moved into the topical discussion on EFT anyway, and quite naturally, based on the previous talks. So let's discuss further any other EFT-related topics.
Gautier has his hand up. Gautier, go ahead.
Yeah, I mean, it's related to this, I mean, it's on this last talk in the first part, the constraint from flavor physics on top operators.
Should we put out the slides again?
Up to you. It can also work without slides. So you include only top operators and constrain them with B physics measurements. I mean, in your conclusion, you mentioned that this could have interesting effects in a global fit, but I wonder what sensitivity would remain if you were to also include B operators. So do you expect that some sensitivity would still remain, or that you would not have enough observables to constrain both top and B physics operators simultaneously?
So you mean a fit of the SMEFT coefficients together with the wet coefficients?
Or only the SMEFT coefficients, but also the B related ones, not only the top related ones.
Okay, I see. Yeah, actually we are trying to extend this. So I mean, this what I showed was basically the proof of concept study, and we are currently trying to include even more observables from B physics and from top physics both. And since by including more observables, we also include different processes where we need to consider further operators. So we are currently doing this with 11 SMEFT coefficients, and yeah, so at the moment we still see a good improvement by using the combination of both, because I mean the beef processes are sensitive to some different operators than the top processes. So combining them also for when using more of the B related operators helps. But I have to say we just consider the SMEFT coefficients that are related to the top and to the B. So the purely B operators we don't consider.
Okay, thanks. Maybe another question on this, unrelated, but still on this topic of the combination of B and top. So once you go to the flavor absorbables, I mean, you have to include full CKM matrix, which is not something, for instance, we do usually in collider absorbable. We take just the unit matrix, and you have to take care of the flavor structures. And the question is then, what assumptions are consistent in SMEFT and that still lead you to having a manageable set of operators to fit? I mean, often, for instance, one imposes, I don't know, flavor symmetry in the first two generations, and one looks for top operators at collider, but now you're also including flavor data, so it's not something that would be consistent to do. So how do you deal with those kind of issues?
Yeah, I mean that's part of the discussion that we have in our group. So of course the B experiments, for example, see deviations from flavor universality, and at the current point we are not yet sure. The first idea is to just leave them out, which make assumptions that do not hold in the top sector. But maybe if we proceed with our studies, we will try to include also them. But yeah, as you mentioned, it's not trivial to do this. Yeah.
Thanks.
Susanne?
Yeah, I have a related question on that discussion. So I'm just thinking the B anomalies in part appear in flavor changing neutral currents, right? In BS transitions, BS L plus and minus. So these should be affected by top operators, right, at the one loop level. So is it really possible to completely separate the B anomalies from doing a top analysis that includes B physics observables?
Yeah, I have to say I'm not completely sure about this. So
you could take the point of view of there's some experimental problem, and we assume that there's no physics in B2S L plus and minus. I think then you could just go with the analysis, right, and neglect or just not consider B2S L plus and minus.
Yeah. So
the penguin is just the same,
yeah,
at least structure-wise, as in B2S gamma. You would catch it if the correction is really from the loop.
Mm-hmm.
So it would be lepton flavor universal in that case, right? So it's rather likely that something is going on with the leptons to explain the anomalies.
Yeah. So yeah, as I said, we try to include even more B observables, but these are the problems that we are dealing with at the moment, and we need to see and how to handle this. So the very naive approach that we are using is that everything that shows some anomalies we exclude in the first round, but then of course we somewhat need to think about how to include this. Yeah, and I think what you mentioned is a very good point.
Yeah, I mean, there are a lot of fits, right, about the B anomalies, but they're all done in weak effective theory.
Yeah.
So it basically would require an interpretation of these results in SMEFT and then just a normalization group evolution to the LHC scale in order to check. And I think in parts this has been done, right? So there are also searches for leptoquarks at the LHC, so this connection has been made in to some extent.
Yeah, that's good. Yeah, I'm not sure. We didn't take a look at these, but I think it's a good idea to go basically backwards from the constraints that are there and compare them what they would yield in SMEFT, and then see how this compares to what we get from our fits. Yeah.
Yeah, and this would involve including lepton operators probably, right? Since these are all taken into account and these provide the best fit results for the anomalies. So this would make a top analysis or a top focused analysis much more broad and much more cumbersome.
Yeah, right.
Thank you.
Thanks.
Any more questions to this one or to the previous one or any of the talks from the session today? There was some discussion still left over from the previous talk, so maybe.
Right. I thought Gautier wanted to make some comments on.
Exactly.
Yeah. I would be interested.
Yeah, me too. So Gautier, let us know. Actually, if Sam is still around and he wants to share the slides.
Sure, I'll go ahead and start sharing.
A quick question, maybe also on that, is on those 2 quark, 2 lepton operators. Do you make? I mean, what assumption do you make about the lepton flavor? Do you assume universality there, or do you only consider, I don't know, muons or electrons? I guess that's specified in the notes, but I didn't read that yet.
Sorry, maybe I misunderstand. What context are you talking about?
So, for instance, on slide 12, you have 4 fermion operators, which involve, for instance, this CTE involves 2 tops and 2 leptons. And I was wondering, what is the assumption you've made about the lepton flavor? Do you consider electrons and muon to have the same coefficient, electron muons and tau to use the same coefficient, or do you treat them separately?
I'm not sure off the top of my head. I would have to look more carefully into the paper and get back to you. Maybe one of the authors can comment though.
Hello, can you hear me?
Yes, very well. Go ahead, Andrew.
Right. Yeah. So yeah, for the 2 quark, 2 lepton operators, they are we assume lepton universality. So basically, we set like the electron, muon, and tau Wilson coefficients to be the same values, like fixed along the same that line.
Okay. Thanks. And to go back to this discussion we had before about the comparison between individual and profile constraints. So maybe it was a naive statistical interpretation on my side, but taking, for instance, slide 13, looking at the first plot that appears there. So that's a 2-dimensional slice in CTZ, CTW parameter space. So my naive interpretation was that if I take this global constraint in this 2-dimensional parameter space, then the bound on CTW would be something like between -4 at the 3 sigma level and +3 or something like this. But now if I constrain myself to the slice in which CTZ is equal to 0, so which would be kind of individual constraint on CTW, then of course the interval or the intersection between my allowed 2-dimensional region and this 1-dimensional line CTZ equals 0 would give me a smaller interval, something like between plus and -2 at the 2 sigma level. So, which is smaller, and that was my naive expectation that it would always be the case that once you impose extra constraints, for instance, that other coefficients are 0, then the allowed interval should shrink and not get wider. But as I was saying, maybe there is some more statistics magic happening that I don't understand here.
Right. So I mean that I agree. That makes sense. It's a little bit confusing, but basically, you know, when you freeze all the other Wilson coefficients and you only fit one, and it tries to, you know, your fit tries to accommodate the data, you end up, you know, you can end up at, you know, away from, you know, 0 or something like that, or, you know, your standard model value as the best fit. And because of the quadratic nature, you can end up with this double minimum that will just naturally, you know, widen the
So that's the case in this specific two-dimensional slice, for instance. This
yeah, right. But then when you consider like the full the full set of Wilson coefficients, the minimum, like I guess the global minimum doesn't becomes very, very flat and can be relaxed back down to, you know, around 0. You know, close to the standard model value. And so because you don't have this, you know, large hump due to the very strict double minimum caused by the single parameter fit, you end up with, you know, in some cases, slightly narrower limits for the profiled case.
Yeah, I guess there's still a bit of magic that I don't get, but that's okay. We don't have to answer all questions.
Sorry, Fabio. I mean, in the
Fabio, you're breaking up.
Yeah, as usual. Sorry. I'll write it.
No. Try speaking. For a moment, it was better.
No, just thinking. Just say that all 4 fermion operators seem to be more constrained in the marginalized fit than in the single parameter fit, and they don't have double minima. I mean, that's at least the table. So can it be with the, I mean, can this due to the NUISA? Otherwise, it's a bit no?
I'm not sure if everybody was able to hear Fabio well. At least I missed the last part.
I think Fabio was asking if this can be due to the nuisances.
Okay, thanks.
I mean, this is Kevin. Maybe I could take a stab at this.
Sure, go ahead.
So, I mean, I do understand how it can be hard to visualize this, but I think, you know, we're used to thinking about kind of the perfect scenario where the data and your standard model expectation align exactly, like if you were doing, say, an expected result. But if you think about any given actual experiment where there's going to be deviations between the standard model prediction and the data, you know, probably statistical, but, you know, if there's new physics in there, that could account for them as well. Then when you do your fit is going to try to accommodate those deviations, and it has at its disposal your signal parameters, so, you know, the Wilson coefficient or coefficients that you're fitting for, and then also nuisance parameters. So the difference between the case where we fix all but one Wilson coefficient to 0 and where we allow all the Wilson coefficients to float, we basically profile the ones that we're not visualizing, is that in that second case, there are more parameters available for the fit to use to try to accommodate a particular deviation. So in this case, our data happens to have a deviation that if you only allow for a single Wilson coefficient, it tries to pull that Wilson coefficient away from 0. But if you give it a collection of Wilson coefficients that it can use to try to match that deviation, none of the individual Wilson coefficients is pulled as far as a single one would be to accommodate the difference between the data and, let's say, standard model prediction. Does that make sense?
So in particular, you would say none of that should be observed in the expected limits.
Yeah, and we do not observe this in the expected limits, only in the observed limits.
Okay, thanks.
I can kind of understand this for the central values. I'm less sure for the range. So for the sigma, actually. Maybe I think it would be nice to look at the pools again, as discussed also earlier by Lisa. It would be nice to see the pools and constraints of the nuisance parameters in some of these specific cases.
Yeah, I mean, I'm not sure. Do you mean, are you thinking specifically of the poles of the Wilson coefficients, or you want to see the full results of the all the nuisance parameters and everything?
I was thinking more about the nuisance parameters in line with also what Fabio asked earlier. Because I think those, if they are pooled or constrained, I think they have a direct impact on what you see here for the interval of the Wilson coefficient. If that's really the explanation, I mean.
No, I mean, I think, so the way I think about it is it's the same set of nuisance parameters aside from the Wilson coefficients between the two curves. And so when you fix the Wilson coefficients to 0, the fit has fewer degrees of freedom to accommodate the data than when you let them float, right? So I think, for example, the difference between, say, having one Wilson coefficient fixed, one Wilson coefficient floating and the rest fixed to 0, and having them all floating is that the nuisance, what we traditionally think of as nuisance parameters, the ones that account for detector effects and theoretical uncertainties, that they'll be pulled less when you float all of the Wilson coefficients, because now you have the Wilson coefficients available also to ease the discrepancies between, say, the particular data that we got in this experiment and the standard model prediction.
Yes, I mean, I completely get the general argument. It still happens that this seems to apply for some of the Wilson coefficients and not for some others. So this is why I think it would be nice to see the pools and constraints of nuisance parameters, essentially for each of the points or some representative points that you have here in this plot.
Yeah, I mean, we can look and see what would make sense to produce, of course, with the permission from the collaboration.
Right, thanks for all these discussions. Any other points to the latest EFT results? Any other EFT questions?
So Fabi is writing in the chat. He's asking if the set of nuisance parameters is always the same in the fits, and then there is a reply from Brent that yes, it is the same set of nuisance parameters.
Maybe if I may, I can ask one more follow-up question on this stuff.
Go ahead.
This is Ken. When you profile over unvisualized directions, normally that leads to a flattening of the likelihood in that particular direction that you're looking at. So still, I expect the limit to be weaker naively, even if the best fit point is slightly away from the standard model. Huh? Was perhaps more of a comment than a question, but I just feel like this explanation of the fact that there's other degrees of freedom that are allowed to float, for me that means that your likelihood gets flatter, and so your interval will tend to get larger. Of course,
I think that's absolutely right, except that probably there are subtleties if there's multiple minima. And if all the Wilson coefficients are free in a fit, I think that, or many of them are free, I think that can be, get really tricky. I think you get nonlinear effects and multiple minimums. I think
it's clear here that when you have the the one-dimensional case clearly needs non-zero values to accommodate the data, and therefore you have a double minimum almost in all cases. If I look at this plot that's displayed right now, probably that's why the outer edges happen to lie outside the outer edges of the profiled case.
Yeah, I wonder also though if there isn't something to be said for normally when we think about nuisance parameters, there's two features of nuisance parameters which make them different from, say, the Wilson coefficients that we're profiling over. One is that there's a constraint, right? You have some external information about what the value should be that pushes them towards zero. And the other is that you tend to have limited sensitivity to the actual values of the nuisance parameters, right? I mean, in cases where you're really sensitive to something, you don't normally think of it as a nuisance parameter. You make it a thing that you're fitting for. So this is really just like saying, if we did an experiment where we looked at the data and tried to explain it in terms of, say, a signal component, single component of signal to having, compared to having, say, multiple components of signal, how would that change the result, right? I think for me, it's thinking of them as nuisance parameters might be making it harder to think about in this case.
Sorry, just to understand, imagine that you switched off the nuisance parameter in the fit, let's say, or in the determination. Would you expect to find what we naively imagine?
So if you turn off the nuisance parameters, what would you naively expect?
I would naively expect that the marginalized must be weaker than the single parameter fits.
Right. So I think that's true when the effect of the nuisance parameters is small and the data and the standard model prediction agree, within, to much smaller than, let's say, the statistical uncertainty. On the other hand, if the effects of the nuisance parameters are not negligible, and some of the deviation between your data and your prediction result from actual systematic differences, right? Your nuisance parameters are basically allowing your prediction to, especially when you think about it in terms of profiling, they're allowing your prediction to morph to try to accommodate the data. If you leave those nuisance parameters out, then that deviation is going to make the force the signal parameter to basically try to account entirely for the deviation between the data and the prediction. So again, the actual, I think you have to be careful thinking about like what you would see on an ensemble of experiments where you fluctuate around your standard model prediction, and what you see from any specific experiment where there's going to be some deviation between data and your standard model prediction, and your fit's going to try to account for that.
Thanks.
So do you have plans to perform similar analysis in other final states?
So maybe that's a question for the talk conveners to answer if they're connected.
What was the question?
Whether you have plans to make similar analysis for different final states.
Things are in progress, but not specifically in this analysis so far.
So you're considering different final states also? Not only multi-lepton?
This specific analysis is only multi-lepton. There's nothing in the works in other channels currently.
This all is, as Nadia is writing, that this is all part of the program that we're trying to pursue. So first we would like to collect, actually this is a very good first opportunity to collect feedback on this particular analysis, and then we take it from there.
Yeah, of course.
Yeah, maybe I could add
that for this, so one is that this analysis has partial data set, as you can see, right?
Yeah, so I can certainly add that, you know, the next obvious thing for the people who worked on this result is to expand to the full run-2 data set. But, you know, one of the big motivations for showing this now is to get feedback from people to see, you know, where things could be improved. So we're absolutely eager to hear from you.
Yeah, I guess we also need some time to look at it and then bring other point of discussions.
Yes, indeed.
Is there any plan on the Atlas side?
Do we have any Atlas conveners still connected that might answer this question?
Francesco is connected, I suppose.
No, Francesco had to leave. Okay, so this will be an interesting question to be addressed at some other time.
Maybe one more, actually, just a general question. I'm sorry, I wasn't able to attend the talk, so it may well have actually been covered. But so you define several signal strengths. Several signal regions, which are just inclusive. They're just it's a counting experiment, right?
Right.
So I suppose an obvious, interesting place to go going forward is to split that up into, bin that in some sort of energy variable so that you can access the sort of characteristic energy growth that's present in the EFT contributions over the standard model.
Yeah, that's absolutely correct. Not easy, but correct.
Any more questions to this analysis?
Yeah, so sorry, can you hear me?
Yes, very well now.
Okay, I actually have a question on the method. So in this is a fit which is by itself quadratic, right? You have included all terms, and you have not tried the linear one, or you don't. You tried, but somewhat didn't work, or what is your strategy there, or approach?
Right. Yeah. So the linear terms are included in this approach as well. It's yeah. We just refer to it as the quadratic because that's it's a quadratic. But the linear terms and obviously the constant term is also included in the this parameterization.
No. Yes, these I seen, but the question is whether to stop at the linear or to go and include the quadratic. And from what I've seen, you included the quadratic, right? Also.
Yes.
But so you didn't do a fit with only the linear.
Sorry, I didn't quite catch that. What was?
I was asking whether you plan or you did a fit also only with the linear terms. I mean, up to the linear terms, let's say.
We did not do that in this analysis. No, but that I guess would be an interesting thing to see the different contribution you get from the different the interference effects versus the pure BSM effects.
I mean, here you have less measurements than you have operators, so the linear fit would be unconstrained in the full space, right?
Yeah, that would be true too, yeah.
That's a good point.
I guess other questions are also, how would you plan to share that 16-dimensional information? Are you only planning to share those one-dimensional intervals, or do you plan to go further than that?
So just to make sure I understand, you're basically asking about sharing in a form that, say, would be useful for doing in combination with other results.
Yeah.
Yeah, I mean, this is something where I think further thought and discussion is required, because it's not clear to me. I think this is a big challenge for this type of approach. I mean, in principle, we have kind of the description of the likelihood in a format that could be included with other things, like the same way that, say, CMS and Atlas combine their Higgs results, right? Putting the kind of low-level description of the likelihood together between two experiments. But I'm not sure, both in terms of technical sense and also in terms of what makes sense in the community, if that's really the best way to go.
I mean, for theorists, doing fits is definitely something that would be useful, because, I mean, otherwise, the only thing theorists can do is go back to your signal regions, look at the expected and the measured, and parameterize deviation themselves, and basically redo with fewer amount of information what you have done.
I guess the question is technical, right? And like also on how to share that
Yeah,
information.
I mean, there is a question of will. Are you willing to move into that direction? And then once the answer is yes, then there is, of course, a discussion to be having with about the technical question.
Right. We have not discussed that internally yet to have an answer.
But can't you put the full likelihood in HEP data? I think.
I mean, we don't have a closed form analytic description of the 16-dimensional likelihood plus all the nuisance parameters, right? I mean, this would be the easiest way to do this would be something like what we've done for Higgs combinations, where you actually have data cards and the full description of the parameterization and the data, and you can combine it. But I mean, that way of working requires a community of people that are going to get together and really dig in a bi-directional way, right? It's not something that you can just push out to the world and then step away from it. The Higgs combination was an effort between CMS and Atlas that was very intense, and people had to invest a lot of time in it.
May I ask a very naive experimentalist question on this analysis? I was staring at the previous slide, and it seems that post-fit you have twice more TTH than pre-fit. How that affects your results shown on the next page? Well, first of all, it's perhaps a bit strange. Maybe it's not a factor of 2, but should be close. Is it something you can explain or you looked at? It's dark red, right?
Yeah, so I mean, so we fit, assuming basically standard model cross sections for everything, and then we just increase the yields with the Wilson coefficients. This is something that we looked at. I think this is basically doing like standard model single strength fits, comparing to those, and they were comparable.
But shouldn't then you see some significant deviation in at least one of your Wilson coefficients that is related to top Higgs coupling? Or
one way to think about this is if we fit this as kind of a standard, let's say signal strength for TTH type of a fit, the factor of 2 that you're seeing, of course, that's the central value, but the uncertainties don't exclude the standard model value of 1 either. This is before you consider what all the Wilson coefficients are doing.
Right.
Now, when we do the the Wilson,
and you don't have good precision, perhaps, on this factor of 2. Okay.
Yeah, that's the way to think about it.
Yeah.
Related to this, how do you separate the TTH and TTW, or you just do simple cut and count in this unlepton NJAS and BJAS?
It's a simple cut and count. I mean, that's part of the reason why we don't, or why we consider them both, and as quote unquote signal. It's because it's very hard to separate them, TTH and TTW, in a single bin, basically.
Yeah, I guess probably more like in other variables, they could have more discriminating power between TTH and TTW.
I mean, yeah, but at the end of the day, I mean, yeah, that's true. But I mean, at the end of the day, I mean, if you're trying to just fit the Wilson coefficients, it's less. I guess it only really matters if you have like a EFT operator that's only really sensitive to a specific process, right? Because otherwise, like, I guess, yeah. I mean, but more discrimination is always discriminating powers is always better for your fit, I guess. So.
Okay.
Any more questions I mean, we have other topics. This is very exciting and very new, and it's really great that all this discussion is happening. But maybe there are also other questions to the other talks from today's session.
So we cut short the spin discussion, right?
Exactly, for example.
It's one of the painful ones, but the one we learned a lot during
So, yeah, when I asked this question, I was having in mind, yeah, basically Alex Mitov talk at the last top working group meeting, where, for instance, difference in BJET definition from the theory side and from the CMS side was discovered and seen to have a significant impact. So when I asked that, I had in mind also what's the status on the Atlas side? Is there the same discrepancy in the BJET definition and more generally in the top-quark definition? And is there effort to look into that also there?
Well, okay, I can tell you what I know. So in the spin correlation paper, there is particle level definition. When theorists Mitov group calculated the prediction at particle level, so sorry, they cannot actually do particle level, right? But they try to reproduce as close as possible our particle cuts, particle level definition. But it still was not precise enough from what we saw. I mean, reproduction of our definition. And that maybe can be the reason of the discrepancies. However, I believe the only possibility is for us to try to go to these parton level jets, which should be maybe closer to what theorists are using, and to make the measurement at that level. It's not being done because, okay, this was measurement with a partial data set, but perhaps with a full data set, this is something we will explore.
But I mean, from what I understood, the lesson of this story was also that the less extrapolation you do, I mean, this was, for instance, seen in a difference in the comparison between the inclusive measurement and the fiducial measurement. The fiducial was agreeing much better with the
right. I totally.
It was seen that
yes.
The less extrapolation you do, the better in general. So going back to the parton level would be opposite to that.
Yes,
I mean, would increase the extrapolation.
Right. So we don't do much extrapolation at particle level. The problem is that theorists in the prediction, they don't use this particle level.
Sure, but at least some things were seen in the CMS comparison, from what I understand, were seen to be improvable. For instance, in this BJET definition, including.
That's right, but we didn't find these differences in BJET.
On the Atlas side, you didn't find such differences.
That's right. That's
Good,
right.
thanks.
One more thing I would like to add, in my understanding, the thing we don't still understand, which is not really the theory thing, is why POIC plus Pythia, which we used as the default, has a much worse description of this delta phi distribution than CMS has with AM low FX. That's, I think, was not yet understood. Well, we just don't have this sample in Atlas, but that will be interesting to understand what is different in MC and low FX that makes data Monte Carlo agreement much better in CMS.
Isn't there also a calculation from Sherpa that includes matching, merging, and electroweak corrections? Wouldn't it be useful to include this in comparisons?
Everything will be useful. we made so many comparisons. Of course, it will be useful.
Okay, because I mean, in PowerEgg we also have this electroweak TT bar corrections as a part of a BSM calculation, actually, but the standard model is included. So I'm not sure whether I mean, maybe this should just be discussed at the next top working group meeting. I don't know.
Yeah, this is definitely something that we can discuss at the next occasion. Yes.
Yes, especially given the expected combination,
exactly,
data combination, then the prediction data measurement will be more precise. And of course, it will be very interesting to compare other things. Yeah.
Do you know if there are more news expected from Mitov and company? I mean, are they still working on anything or in this direction?
Well, to my knowledge, they provided everything they planned.
Okay.
All right. As you can see, we are sharing a slide with other questions. And we just went through the spin correlations, which we had on our list anyway. And we had a question from Nadia regarding top mass and renormals. She can speak actually. So we thought we would bring this question up.
Sorry, Jirka, I think it's this scale uncertainties for pole mass and MS bar scheme.
Oh, okay. Yeah, right. This one. All right, so yeah, can someone answer this? I guess this really goes to the theory side then.
Yeah, I think this was related to this claim about scale uncertainties being larger near the threshold when the MS bar mass is used rather than the pole mass. Is this correct? And I don't know the answer to that, but perhaps someone knows.
I can try to bring up the slide if I remember it, but it may take me a minute. Sorry, so it was Serena's talk, wasn't it?
Yes, it's Serena's talk.
It's not. I'm moving to the slide that I can share my screen again, proper one. Yeah, here we go. It was the table. Let me reshare again. I'll stop. Share again. And yeah. So we can see. And it was regarding
No, I think it's related to this theory thing below. Or here.
No, it's related to this. Exactly.
Right.
To this comparison.
You can also see in the numbers below this theory. Different.
Right. Yeah. So CMS observes different trend, larger scale uncertainty in the pole mass than MS bar. So that's the core of the question. And CMS justifies it as a result of better convergence in perturbative theories with MS bar scheme. So does this make sense? And then the question continues whether this could be because of additional jet that changes the picture.
Well, it may depend on the method, right? CMS observes the opposite trend using which method?
That is not part of the question.
Right.
Hello, do you hear me now?
Yes.
Okay, thank you. Sorry. So yeah, indeed, I mean, the measurement that I'm talking about is about using the TT bar inclusive cross-section to extract the pole mass and MS bar bands from CMS side. I understand that there probably the effect of the threshold thing is somehow diluted. Maybe it has something to do with that, but I would like really to understand what is the theory hint on that.
Yeah, exactly. The question is it expected or not, right?
Exactly.
Right.
Exactly. I mean, what?
I mean, it's expected that in the pole scheme, you have the renormal ambiguity, which enters also the total cross-section, while if you use the MS bar scheme, you don't have this pole renormal ambiguity, and as long as you're inclusive, you're not introducing power correction. So as long as you don't put cuts or threshold, this is expected, I would say.
You mean it is expected that the uncertainties on pole mass are larger than the MS bar mass?
Yes, because
Okay.
In the pole scheme, the perturbative series is not really that converging. So this is somehow, if you use scale variation as an estimate of perturbative convergence, this is sound. This is totally expected thing.
Right, and in this atlas measurement, we are essentially sort of differential because we are using a distribution that is sensitive to threshold effect. So then that argument would not hold here, right?
I mean, if you start being differential and start putting cuts, you are introducing other sort of power correction related to the way you build jets. So in that case, I don't know.
Okay, but at least, I mean, thank you. I mean, it at least gives some hint into that, because to me, at the first glance, it was a little bit confusing. I don't know, maybe at some point when we have similar measurements on both sides, either differential or inclusive, we can compare better.
Well, the inclusive we have, but we only have the pole mass, right? From ATLAS and CMS, we don't have the running mass from the inclusive cross section from ATLAS. Is that correct, Lisa?
Yes, that's correct at the moment.
Mm-hmm.
Okay, thank you. I think I'm fine. I mean, maybe we should first see, I mean, what comes out from future measurements. Thanks.
So you should be back to sharing the questions that we have.
But by the way, I'm reading the paper on this, and it's written in the paper that the scale that the scale variation has a large impact on the MS bar mass scheme, as already observed in reference 17. But perhaps reference 17, in fact, is okay. Yeah, is some a kind of phenomenological paper, but I think it's related to the same method. So perhaps it is related to the method.
Okay, perhaps one last very quick question. This is a question actually from me. For the top width measurement in ATLAS, the uncertainty on the slide was claimed to be was it 0.6 GeV or something like that, for a mass of MT 172.5. And I was wondering whether the uncertainty on the top mass actually is propagated into the uncertainty on the top width, because in this reinterpretation of the measurement of the TT bar and TW interference effects that was measured in the MLB min-max distribution, what we noticed, so myself and some colleagues from ATLAS, that actually the further away we move from the bulk of the distribution, which is quite a good sensitivity on the top mass, the lower top mass uncertainty on the top width. So we get the lower mass, lower uncertainty on the top width. Is this something that you also observed in these measurements, or not at all? I mean,
well, if you look at this MLB distribution, it's actually cut. The high tail, which you found the most sensitive in the paper you are mentioning, was cut out to avoid dealing with this interference effect.
Yeah, so if I can answer, hi, this is
Okay, Thomas, sorry, I didn't know that you were connected.
Yeah, so you are completely right that we basically only allow MLB up to 150 GeV exactly to get rid of these NLO and off-shell effects. And the top mass is fixed in the result, but we also provide the values for other fixed values, so plus minus half a GeV. So we actually quote 3 different values in the conf note, and you will see that this half a GeV effect on the mass has only around 100 MeV effect on the width. So it's quite stable in this range.
okay, yeah, that's quite interesting. Yes, as you pointed out, in this respect, the two analyses are completely in different portions of the phase space, and I'm wondering whether our observations may have to do with the fact that maybe including the whole, or the whole of the distribution may reduce the sensitivity on top mass somehow. I don't know, but yes, thank you. That's very good to know.
All right, we've had an hour of discussion. So the thing is, what we do now, I think the room's still left for us, so we can go ahead. We can change topic. So anyone has any suggestion, question? Yeah, it's been a long meeting, but I think full of very interesting results, and we've had a nice discussion. Okay. Yeah, I think it's time to conclude on all time zones. Unless there's something really urgent, last call for a question. All right. All right, so thanks everybody for this very nice session. Thanks for having connected and having stayed in such a number. I think this is quite a fair amount of people. There was above 30 participating, and we had many more connected during the day. Let's not forget about the poster session tomorrow, and of course our session, which actually starts early morning tomorrow, about 8 Sun time.
I would like to add that the Mattermost chat seem to now be a little bit more active. So feel free to catch up on discussions there and ask questions there and discuss as you see convenient and fit.
Right. So thanks everybody for participating in the discussion. We had people connecting just for the discussion or coming back to the discussion. So many thanks for that. And yeah, you all have a good night and see you and hear you tomorrow. Thank you and bye-bye.
Thank you.
Thanks. Bye.